Hi everyone, my name is Sergio Sanchez. This is the tutorial for Geospatial Public Policy Analysis with GeoPandas. I'm going to have a quick presentation at the beginning, and then we're going to go over some of the tools and the data sources that we'll be using for the tutorial. And then I'm going to show you how you can access the code and how you can run the code. And then we'll get started doing some Geospatial Public Policy Analysis. All right, so who am I? My name is Sergio Sanchez. Like I mentioned, I'm a research associate. I was a research associate at the Higher Ed Center at PPIC, the Public Policy Institute of California, when I first submitted the talk. I was doing a lot of public policy analysis of California higher education public policy, obviously, and it focused mostly on developmental education in the community college system, who transfers, who doesn't transfer to a four-year institution. I was doing some migration policy too and economic mobility. And now I am a data visualization analyst at Aluma. Aluma is a social enterprise in the healthcare and social services space. I also have this personal project called Tacos de Datos, and it's a place online, it's a community online where you can share your best practices and cutting edge knowledge in the field of data analysis and visualization in Spanish, so that all this knowledge that we have, all these advancements in tech that we keep seeing every day happen, don't stay in the English speaking world only. Well, that's the goal, right? So you can find me on GitHub at github.com/Chekos, Chekos, as you can see in the screen. On Twitter, Chekos WH. You can, and if you're interested, you can follow Tacos Datos 2 on GitHub at github.com/tacos-de-datos, and on Twitter at Tacos Datos 2. So what do? The overarching theme of what I try to do in my professional life and everything that I do work related is to facilitate knowledge transfer. How can I get an idea from mine or my colleagues' brains into yours the fastest way, the easiest way? So it's making complex topics easier to understand, and it's fairly obvious how that plays out in a research institute, right? We would look at numbers, we would find trends, we would explain those trends to the legislature, and hopefully they would make an informed decision, and they would make a much more informed decision after that, right? In the data visualization world is still more or less, how can I make this easy for you to understand, right? How can I present complex information so that you understand that the fastest way possible? And in general, it's just making research more transparent, reproducible, and accessible, which I hope this tutorial helps you do. This has many implications, but one of the main reasons that I do this is that so that anyone who wants to do this can do it if they want to. They don't need anything else. If they have the will and they have access to a computer and Python, they should be able to do what you're doing with Python, right? So because of that, we'll be using certain tools in this tutorial, and hopefully you take some of these practices and implement them in your everyday workflow. So what will this tutorial cover? It's essentially step-by-step from start to finish. How would a researcher go about answering a research question that entails some geospatial analysis? So we're going to be looking at how I organize my projects in general, the workflow from start to finish, data cleaning, then doing this and doing this and doing this, and how to use pandas and GeoPandas for this type of analyses, which is probably what most people are here for. What can you do with GeoPandas? Panda sounds awesome. You're adding geography to it. That sounds cool. What can we do with that? So we'll be going over that, and more specifically too, we're gonna learn how to manipulate geographies, shape files using GeoPandas. Who is this tutorial for? Beginners. We'll be using my binder, so you don't even need to install anything. There is some expectation of Python knowledge. I'm not going to teach you Python from scratch. We'll be using Jupyter. We'll be using pandas and GeoPandas. So if you have had some experience with it, is obviously going to be a big advantage. But we're not going to be touching on complex or more advanced topics. I don't think we won't even write any functions, right? Like it's going to be very much scripting, step by step. First you do this, then you do this. So beginners, people just getting started should be able to follow. If not, I'll be happy to help you out, and you can go on GitHub for the repository, submit an issue, or reach out on Twitter, and we'll set up a way to answer any questions that you have. If you want to learn a bit more about pandas before this tutorial, you can go to my other tutorial that I did last year at PyCon 2019. It's on GitHub under github.com/checos/analyzing census data. It's a tutorial on analyzing census data with pandas. That one goes more into detail, step by step, what can pandas do. So it'll be very helpful. The link for YouTube is on it too, and I'm sure you can just Google it. So what tools will we be using? We're going to be using Jupyter Lab for our analysis. This is where we're going to have all our Jupyter notebooks and the work, and just everything is going to be in Jupyter Lab. We're going to be using obviously GeoPandas and pandas to manipulate data. Pandas helps you analyze data. GeoPandas is pandas plus the ability to manipulate geographies and to implement geographies in your data analysis. We're going to be using Geoplot, which is, if you've heard of Seaborn, which makes Matplotlib visualizations kind of like pretty by default, that's what Geoplot is for maps. It's kind of Seaborn for maps. And we will be using a command line interface, a command line tool by the LA Times data desk. It's called Census Data Downloader, and this is just going to be so that we can automate. It just facilitates us getting the data into our computer, and it's good practice. It's a really cool tool. The LA Times is doing some really cool things. You should check them out if you're interested in this type of stuff. So what data sources will we be using? We're going to be using IPEDS, which is from the National Center of Education Statistics, is the Integrated Post-Secondary Education Data System. Integrated. Yeah, I don't think anyone knows what IPEDS stands for, but everyone in the higher education space, research space, knows IPEDS. And we'll go on the browser and explore more about it in a bit. We're also going to be using American Community Survey data from the census. That's the yearly survey the census conducts. That's what the Census Data Downloader tool is for. And we're also going to be using Tiger shapefiles by the census. These are the quote-unquote official shapefiles that the census provides for us. Next. So what questions will we be answering? Like I mentioned at the beginning, we're going to be going step by step. How would a researcher go about answering a question that has a geospatial component? So what are those questions? We have essentially 3 questions, 2 main questions plus like the map. The first main question, the first research question is, how many higher education institutions are found in counties with majority underrepresented groups? So these are groups, these are Black and Latino folks, Native Americans, places who have been historically underrepresented in higher education. So how many higher education institutions are there in these counties that are majority underrepresented, right? And what are the characteristics of those institutions? Do they vary from institutions in more affluent or more on those other counties? Second main question, are there any counties that don't have any higher education institution? These education deserts. If you find yourself in a county that doesn't have any higher education institutions, what if you wanted to go to a higher education institution? That means you would have to leave, or maybe you don't even think about going to a higher education institution since there's none around you haven't seen one, etc., etc. These are obviously assumptions, but are there any education deserts here in the United States? And what are some of the demographic characteristics of those counties? So if there's no higher education institutions in that county, how is this county different from other counties in the United States? And we're using county is an arbitrary geographical level. We could go up to a state, but obviously every state has higher education institutions. We could go down to a census tract, which is a very small unit. But then you lose some of the demographic data that goes with it because that's not publicly available at that granular level. And then we're going to make some maps. So what parts of the country are left out if you create a 10, 25, 50 mile radius around higher education institutions? There's some research here in California that shows that most people, the typical student, goes to a higher, when they go to college, they go to college within, if it's a state school, I think around 25 miles. If it's a UC, because this was in California, it's 50 miles. That's the average, the median distance between the college and the home of the student. And if it's a community college, they don't go further than 10 miles mostly. So those are the questions we'll be using, and we're going to be creating some maps along the way. And with that, let's get started on going over the tools and the data sources that I mentioned. So this is the NCES website. It's nces.ed.gov/IPEDS. This is what we're going to be using for our data. As you can see, is the primary source of information on U.S. college and universities. If we go here, give me a second, sorry. We go join in. What we're going to be using is, not join in, sorry, my bad. Use the data. We're going to be using this tool. This has already been downloaded for you, and I cleaned it up a little bit because the variable title, the column names are horrible. But as you can see, you can create groups and you can look up institutions by whether they grant a degree, what sector they're found, what are they, public, are they private, are they in a specific state. And for each institution, you can find a lot of information. You can find how many people go there, fall enrollment, how many people stay throughout the year, what degrees, how many degrees do they give out, what are the graduation rates, what's the average price, student financial aid. It's a lot of information. It's really interesting if you're, it's really great if you're interested in that type of information. We're also going to be using the census data. We're using American Community Survey data through the Census Data Downloader tool, but you can also go to data.census.gov and look up information. They have tables for everyone, and they have a lot of information here. So check it out if you're interested in census data, which is pretty cool if you ask me. We're going to be using Jupyter Lab, like I mentioned. If you haven't heard about it, it's a web-based interactive development environment for Jupyter notebooks. You can have code and data and rich text in the same file, which is pretty cool. We're going to be using MyBinder to run our code so that you don't have to install anything. It's all going to be on your browser. I'll show you this later. You're going to have the GitHub repository and the link, and all this does is spin up an instance of Jupyter Lab on your browser with all the dependencies already installed. We're going to be using pandas, obviously, for data analysis. We're going to be using GeoPandas for the geospatial analysis aspect of our research. make working with geospatial data in Python easier. That's what we're looking for. This GeoPandas is what allows you to read in shape files and geometries into a data frame like you would with a regular CSV, for example. We're going to be using Geoplot for maps for geospatial data visualization. It's a high-level geospatial plotting library. It's an extension of CordoPy and Matplotlib, which makes mapping easy, like Seaborn for geospatial. It's pretty cool. It just makes everything a little bit easier. Map making a little bit easier. And like I mentioned, we're going to be using the Census Data Downloader tool by the LA Times. What this does is it allows you to run this from your terminal. Census Data Downloader, give me the median age for all the states, or median age for counties if you want to change that. So, or for year 2010 or 2011 or 2018, median age states or counties or divisions, etc., etc. And you can create some really cool maps with the data that you download from here. They've used it for some of their own data journalism. It's really great tool. It's a really great tool. But to use it, you're gonna need a Census API key, which is very easy to do. You're gonna go to the Census Data Downloader repository, github.com/datadesk/census data downloader, and in the README, you're gonna get to this part. You're gonna click on this link, and you're gonna request the key. This takes let's call it this takes like 2 minutes. Actually, it's really quick, so you should get on that right now. So we're gonna use it later in the video. And while I have you here, I just want to take a second to remind you, if you're in the United States, please go out, and if it's still 2020, please go out and fill out the census. It's very important, and it is going on right now. You can go to census2020.gov and respond. Even if you haven't gotten anything on the mail, even if you lost the letter in the mail, you can answer this online. And it's just, I cannot emphasize this enough. This is really important for everything here in the United States. So please, if you're in the United States, if you live here, regardless of anything else, if you're living in the United States, please go to 2020census.gov and answer and fill out the census if you haven't already. Okay, and with that, we're gonna get to working on the code. Alrighty, so let's get started with the tutorial, with the actual code. You're gonna want to go to github.com/geospatial-public-policy-analysis-with-GeoPandas. I know it's a long name, but I was trying to be as forward as possible. You could also just go to github.com/checos, and it's gonna be right there, the second pinned item. So that's way faster. And what you're gonna want to do is we're gonna click here. We're gonna be using my binder. I'm gonna add instructions for. There will be instructions for how to run this locally, if that's what you want. And in the my binder folder, there's the environment file with all the dependencies. So it would be, you can run this locally. It's just for simplicity. We're gonna be using my binder to follow along on the tutorial. And you're gonna click on the badge. It's gonna take you to this page, and if you click on the show, it's gonna show up. It's gonna show you the logs. And because I already ran this once, they have a Docker image already built for this GitHub repository, so it'll be fine. But if it doesn't say found built image, it probably means that I just changed something in the repository, so they're creating the image. That's gonna take a little bit, so you're just gonna have to wait, but it will get there to you. And from here, you just gotta wait. It usually takes less than a minute for large repositories or repositories with a lot of dependencies. It takes a little bit longer, but from my experience. So what you're gonna see here is it takes you directly to Jupyter Lab. If you prefer the notebook environment, you can change this in the URL, the last part, the LAB for lab. You can just delete that for the Jupyter, the classic Jupyter notebook view, or in help, you can just click launch classic notebook. I don't recommend it. We're not going to be using that, but I'm fine. So this is the basic structure of the folder. We have a authors MD, which a license, the README file, which is this, and it will be updated to show the installation steps, etc., etc. There's a data folder with 4 subfolders: external, interim, processed, and raw data. And here's the definitions for each of those. There's a docs folder where you can drop any documentation, PDFs, or any other type of documentation that you use during your workflow. The notebooks folder where we're going to be working on. Then there's a reports folder for whatever markdown or the manuscript if you're writing a report. Within that, there's a figures folder. So if you produce any images, which we will be doing with, we're going to be creating some maps, they're going to go directly on figures. And then there's a source folder for whatever code you produce that you don't want on your notebooks, any scripts, any helpful code that you either get from somewhere else or models that you create, anything that produces the visualization that you want to do, anything that you want to extract from the notebook, you could just throw it on source for this, so that it's in one organized space. This is based on the cookie cutter template for data science, which I changed a little bit. It's based on the reproducible science cookie cutter by MKRAPP. Essentially this, I just changed it a tiny bit. I don't have the bin, I don't have the config. This is what I use for all my projects, just so that it's standardized and I know exactly where the notebooks are gonna be. I know exactly where the scripts for data analysis. I know where the scripts to create visualizations are gonna go on. So standardizing your workflow is very useful in the long run, especially if you have an idea and then you want to try something and then you forget about it, and in 6 months you want to go back and be like, oh, I had that one idea I was testing. Alrighty, so we're gonna go on notebooks. You might have noticed we have a solutions folder, which is not here in the project organization. This is for this repository for the tutorial. This is where I'm gonna have the solutions, the notebooks that we create today, and those are gonna be, I'm gonna add more explanations to everything that we're doing step by step, and links so that you can follow along and learn more about whatever we're doing. And so you can check those out. I don't recommend looking at them right away, right? You want to try to do all of this on your own, and then you can check the solutions. Alrighty, one last thing before we get started. Because my binder is an instance on the cloud somewhere, it will go to sleep. It will turn off after 15 minutes of inactivity. So you should be running something every 10 minutes, every 10 to 15 minutes at least, so that your instance doesn't die, right? And you might see me code for more than 15 minutes, but you should pause for 15 minutes at a time. So, but you should pause the video every step and then write the code along, or put it on the side and start writing your code. Okay, so we're gonna go in the notebooks folder, and first things, we're gonna create a markdown file with the steps that we're gonna be using, right? So that we're gonna be doing. So the very first thing in every research project is data cleaning, getting the data, cleaning that data, getting it ready for analysis. It's like 90% of the work that I used to do day to day as a researcher. So let's write this down. Instructions. Step 1, data preparation. We already acquired some data for you, and so that is ready to go, and then I'll show you in a bit. Data preparation. Step 1, we're going to be preparing the institution data. Institutions data, then the county level data from census, and then we're going to keep it simple, then data analysis, right? And obviously this is quote unquote a living document. We're going to go back and add any other steps that we want to do in between. Data analysis, research question 1, research questions 2, research question 3. Okay, let's save this. We'll just call it readme, so that when we throw that back in GitHub, is ready to go, right? It will show up as the default. So because we're going to be working on data preparation, we should explore what type of data we have already. If we go on the data folder in external, you'll see that I have included 2 zip files. This one is from IPEDS. This is the institution's data, and TL is the tiger lines, those US Census county shape files. I'm gonna go on data. I have already, in the processed file, I have included a script on the GitHub repository on source data. There's a data cleaning.py that you don't have to worry about this, but it's essentially going through that zip file and processing it a little bit. It deletes an empty column that comes with IPEDS data. A lot of the time, for some reason, it always comes with an unnamed column, and then the number varies depending on the number of columns, variables that you get. And then it's just cleaning up the names of the columns just a little bit, because it's you don't need to worry about that for this tutorial. So I just included that for you. And then the geodata cleaning as well. It's not really cleaning. It's just opening up that zip file and then creating, essentially just extracting it. It's not cleaning the data. And those were already ran for you when you open up your when you go in my binder. But if you're running this locally, you're gonna have to run those yourself, and you can do that by just on your terminal tapping Python and the script, right? So on process file, you see the process data for the institutions. Kind of looks like this. It has some institutional names, the state they're in, whether they're public, and at 2 or 4 years, whether they're they should all be degree granting, but whether they're mostly bachelor's degree or not mostly bachelor's degree, their address, longitude and latitude, whether a tribal college or a historically black college or university, some more statistics about this. Right, we'll explore it in in our first notebook. And then the geodata is just a shapefile, right? And that one can be read onto GeoPandas directly. So on the notebooks, let's create our first notebook. And first things first, you should always rename it to whatever you're going to be calling it. I'm going to call it Data Prep Institutions. Save that. And the very first thing you're going to do is import pandas, obviously, because that's what we're going to be using for data analysis. We're going to be using pathlib for paths so that it works both on Windows and Linux-based systems. You may have noticed that I included this little script. It just has a function called tree that displays the tree, the directories tree. I call it tools.py. You might see other people use utils.py. As I just happen to do this because this is how I learned. I don't come from software development. I come from social science, so I don't have. So that's just how I learned myself. So we're gonna import that function so that we can use it, right? And then we're gonna import this datetime function because you might not, for whoever doesn't have experience with version control, right? If you're following this along, you might have experience with GitHub, and you might already know Git, and you may know version control. But a lot of people coming to tech from academia and from social sciences, we don't really use version control for just in generally. And so our way of version control is just tagging a date at the end, or adding like _final _final, and it's not the best way to do it, but it's one way to do it, at least, to have at least some sort of version control. So what we're gonna do is use the today function so that it will create a today string f time, and we're gonna do day we're gonna use B, which is the letters, then Y, and then we're gonna call it so to make sure that it worked. Okay, so today is the 24th of April of 2020, and then what we can do is just tag this at the end of any CSV file that we produce. Again, this is not the best way to do it. You may already know version control if that's how you're doing it. If you already know that, you should do it that way. But if you don't have any experience with version control, at least throw that in there to differentiate between the same versions of the same file. Okay, so we're gonna create the paths for our data folder. So we have raw data equals path data raw, right? And what this is doing is just saving us so we don't have, we're just doing this so that we don't have to explicitly type /data/raw/ whatever the file name is every time we want to call something, we want to read something from the raw data file. And because it's path lib, and then the path class will be, it works both again on Windows and Linux based systems, so you don't have to worry about which way the slashes are going. So we're gonna do one for entering data. I like to do this for all the data folders that we have, but even if we're not gonna use all of them right now, we're gonna do a processed data and the final data path and the external data path. External. Ran? No problem. Alrighty, so excuse me, I'm reading my notes to make sure that we get everything. We're gonna use this tree function to see what we have on our external data folder. You can click tab for autocomplete, and we see that we have the zip files that I just showed you, right? If we go to processed, you can see this again. You can see that we have the process data from the institutions, which is what we want here, and the shape files for our counties. And this checkpoint was just created right now when we opened it in Jupyter Lab. Okay, so we're gonna read into a data frame using pandas. Pandas read. If you do tab, you can see all the options. There's a lot of options. I love pandas. What we're gonna be using is CSV because it's a CSV file, right? Now, this is a cool thing about path in Padlib. You can do processed and then slash and then processed data.csv, and that just works. Data.head. So here we have a data frame from. We read that. We read that CSV file, and we have a data frame, so we can actually manipulate it and play around with it in pandas. Another way to do that, I'll just show you real quick. Processed data. Another way to create these paths, you can do join path processed data.csv, and I'm just gonna run it so you see what happens, and it just works. And if you're running this in Windows, it would be showing you the other slashes. So you can do that join path, or you can do the slash. I like the slash. It's just kind of cool. Okay, now that we have our data frame, it's a little bit hard to read all the columns that we have. It skips some. These are really long names. So one thing that I like to do is transpose it. So data.head and then .t, and you're not actually transforming the data. All you're doing is getting a transposed view of it, right? So instead of the columns going left to right and the rows top to bottom, you switch them around, and this way we can read the names of the columns right here, and it's just a little bit easier to read, especially for these really long ones, right? Grad rate, bachelor degree, 6 years, native Hawaiian or other Pacific Island. That one over here would have been, this is it, right? It's a little harder to read. So you'll see that we have the unit ID, the institution name, the state they're in, the sector, which includes whether they're public or private, and whether they're 2-year or 4-year or more. The institutional category, which we talked about a little bit, street address, institution name alias, so if they're known as something else, this is where it shows up. Institution name, it seems that we have a duplicate column, and pandas does this automatically. We'll just add a .1 to differentiate. Longitude, latitude, some characteristics of the institution, whether they're historically black college or university, a tribal college, the percent admitted, the percent admitted for women, the percent admitted for men, the percent of total enrollment that are American Indian or Alaska Native, they're Hispanic Latino. There's a lot of statistics that we have included for you to play around with. We're gonna choose what characteristics we want from this large data set, and we're gonna create a analytical data file, a subset from this master file, so that we don't mess around with it. This one's already prepared. It's good to go. It works for what it exists for. So what we want is to create a subset that's the working file for our process for this specific project, right? So what we're gonna do is create a list of variables of interest, and I'm just gonna call it VOI for variables of interest. And we're gonna create a list out of these columns, what we're interested in, right? So we want the institution name, we want the longitude and the latitude, and scroll, right? Because we're gonna, this is geospatial policy analysis. We want the FIPS state code, which is where the state is, and the value for state is. We want the sector, which we talked about a little bit. We want the total enrollment, and we want the full-time enrollment and the part-time enrollment columns, right? These are right here. So this college has 150 people, and 108 of them are full-time and 42 of them are part-time. This is Nakota College in Montana. Interesting. So these are the columns that we want for this specific analysis for what we were going to be doing today. You can choose to add, and this is why I included all these other variables. If you want to do some other analysis, if you want to see, for example, what's the graduation rate for men to get a bachelor's degree within 6 years, you get this here, right? So this school, 64% of men that are getting a bachelor's degree get it within 6 years, right? 64, that means what? 36% of men that come to this school don't get a bachelor's degree within 6 years. That might be the dropout, or it takes them 7 years, right? Or it takes them 8 or more years. So we're gonna run this. Now that we have this list of columns, we can grab that subset. If you do data, this is how you will grab a subset in pandas. You could pass it a list of columns in the square brackets, head, and now we have this. Now we have a subset of this. This we could have done square bracket again, institution name, sector, right? We could have passed it directly, but it's easier. You should take that out and make it a list itself. And I chose to do it like the long way, with what I call the long way, because maybe I don't want this anymore. I just commented that, right? Or maybe I want another one, and then I want it in this specific order, so I can just drop it here. So it's just easier to manipulate. So now that we know that this is what we want, we don't want only the first 5. We're gonna create a copy of this data frame. We're gonna call it working df. So we're gonna send it to something else. It's gonna be the data frame, but we're only gonna grab the variables of interest. And what we're gonna do is make a copy. And we do this because if we don't do this, if we just say, okay, it's a data frame and these columns of the data frame, and then we do something to the working data frame, if we manipulate the data, if we change it somehow, we're gonna get a warning from Pandas saying that you are manipulating essentially kind of a window into the other data frame. And that's not what we want. We want a deep copy of it. We want a whole other data frame. So we're copying that. And PDF. You can always do that head just to check that everything is running smoothly in Pandas. So what we have here is the sector variable is essentially 2 variables, right? It's whether an institution is public or private, and whether an institution is 2 years or 4 year or above. So what we want is to split that into 2 columns. And the way you do that is working df. First, this is how you would grab a column from Pandas. You do the square brackets like we just did for the multiple variables. But if you don't pass a list, you pass the name of a column, sector, it returns it as a Pandas series, right? And then you can see that it looks a little different than the data frame. So what you want is, so these are all strings, and we know that in Python you can split a string with the split method, right? Grab that, split on the comma, blah blah. So you have these. So what we want is to be able to apply these string methods to this series, to each element here. And the way you do that in pandas is you use the string accessor. So you got to do .str. That lets pandas know that you're going to do a string method on a series. And what we're going to do is split on the comma and the space, because we'll just take care of that right here. And let's see what happens. So now you have a list, right? So it's splitting to two elements, but it's still returning one series, but instead of each row having a string, you have a list, and that's not what we want. In pandas, you can pass the argument expand equals true. Bam. It creates, now you can see that the format changed. It creates a data frame with two columns, one for each of those elements in that list. And what we want is, just like we did this here with the square brackets, that's how you grab a series. What you do, if you want to grab a series, you pass its name at 0. Now we get this one. We pass 1, we get the other one, right? And what we want to do is, let's just be lazy and copy it, paste it. What we're gonna do is assign it to another series. We can call it, what are we gonna call it? We're gonna call it control. So whether it's public or private, and the other one is gonna be level, whether it's 2 years or 4 years. I'm gonna run this, bam. We don't need this, so we're gonna delete it. So we do working df head again, just check that everything's working. And you see that we have two new columns, control and level, and these are based on the sector column, but we split it. Okay, so now that we have this, we don't really need the sector column, right? And how would you drop a column is with the drop method. Drop columns sector. Let's run it. You see, now it dropped it, and we have a pandas data frame with 3,751 rows, 9 columns. So this is returning a pandas data frame. So if we save it to the same, it's going to overwrite itself, and it just deletes this past work data frame, and it just saves it the way we want it. You could do also working data frame columns sector in place equals true, and that instead of returning a data frame it would just save on itself. A while ago I saw a talk by Mark Garcia from Pandas, who was suggesting that maybe you shouldn't do that. There's some internal stuff going on with the in place. So ever since then I've just been doing it this way, just being explicit of overwriting itself. But it works with in place too, if that's how you want to do it. Okay, and that was pretty much it for this. We started with a master data set. We grabbed the columns that we were interested in. We dropped the columns that we didn't even want anymore, like sector. And now we have a analytical file, a working data frame that we're going to be using for the rest of our analysis. So now that we have this, let's do in markdown. And you can see that I didn't change it over here. I clicked escape so that I was selecting the cell and not inside the cell. Then I click M, that changes it to a markdown cell. And I'm just gonna make a checkpoint, announce a checkpoint. And the way we're gonna do this is working df to CSV We're still gonna want to save it to process data. And let's do it the other way now. Join path, and we're gonna name it institutions data.csv. Right? And we don't, it by default, pandas, let's do shift tab to see the options. You'll see that pandas uses index as true by default. So it would save a column that name it index, and it would save it, and it will save this over here. We don't want that. We don't need that. So index equals false. Let's see what else. Encoding says none. I like to encoding. You use UTF-8 to make sure that we don't lose any special characters. My last name has an accent, a tilde on it, and it always gets lost if you don't use UTF-8, or if you use something else. It's a mess. And some of these colleges might have some special characters, so it doesn't hurt to be explicit. And we're gonna run this. Voila, we got the first notebook done. So now we have in our data, you'll see that it was last modified seconds ago because we just saved it. And processed, now we have institutions data. This is what we're going to be using in our other notebooks. Okay, so we have the institutions level data. Now we have county level data from census. So how are we going to do that is using census data downloader. We don't have, I didn't include the data here. It's not an external. It's not in trim. It's not in the process data, which you saw. It's not anywhere else. What we need to do is use the census data downloader tool, which is already installed in your environment, to acquire the data from the census. And we can go to GitHub, data desk, census data downloader, to see how one would do this, right? So what's available, a lot of these tables we have already installed it in, and if you ran the installation instructions and you're running this locally, it's in our dependencies file, in the environment file, so you should have it. And the way it works is, first you need to export. You don't have to, but it's just gonna make things easier. Your census API key. This API key, like I mentioned earlier in the video, you can get from the census. You gotta sign up, give them your email. They're gonna send you one right away. And after that, we can start using it like the census data downloader. Pass the year you want to use, what you're asking for, and at what level do you want it, whether states, counties. We want county data, and what we're going to be looking at is demographics, race, ethnicity. So we're going to use race for here. And the way we do this, we go over here. First step, export census API key and pass your API key. I already received mine. You're going to get an email like this that says, thank you for your interest. Here's your API key. We're going to grab that, Command C. I'm going to copy it. Over here, I'm going to do export census API key equals, bam. So now it's ready to go. So what we're going to do, and you saw that how I launched this. You can click on this plus button over here. This is how you would launch another notebook, a console, a Python console, create some other files. You can launch a terminal from within Jupyter Lab. So the way this works is census data downloader year equals 2018, which is the latest. Data dir is gonna be, because we're at the top level directory, is gonna be on data external. And what we want is the race tables for race, ethnicity, demographics, and we want it at the county level. We don't want states, we don't want tracks. County is what we're going to be working on. And we click enter. Oh, it's not county. Oh yeah, duh. Counties. Click enter. This is going to take a little bit. Dun, 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 dun. There you go. So this is downloading all these variables for each county, right? So the universe is all of the people in that county. Universe annotation, whether there's an annotation, universe margin of error, and the margin of error annotation. The numbers for people who only identify as white, people who only identify as black, American, Indian, Alaska Native, Asian, Native Hawaiian, Pacific Islander, other 2 or more races, or Latino. It's done. Okay, so we can go check in data. This was an external, and you'll see that it created a processed and a raw folder. The raw folder has the names from the table. It has this is from table B03002, and all these column names, they don't make sense to any human. That doesn't work at the census. But if you go to processed, they made it easier for us to work with, right? They created the white alone, the black alone, and the Indian and American Indian and Alaska Native alone numbers for us. So that was it. Now we have used this command line tool to get data straight from the census. So what we need to do now is process that data, prepare it. So we're going to create a notebook. Let's call it data prep counties. And what we're going to do is we're going to import pandas as PD, like we do from path label. We're going to use path again from tools. We're going to import tree. And if you may have noticed that I'm already doing exactly the same thing as I did on the other one. So what you can do, this is a trick that you can do in JupyterLab. This is why I like JupyterLab above the classic Jupyter notebook. First, you can grab this one, put it on the side, and you have 2 notebooks side to side, right? And what you can do is grab this, click Shift, highlight these cells. You can click Copy, or you can just click the key C. I'm gonna do copy. You can go over here. You can do paste. Boom. And I took the delete one. You can just I use X to cut it to the first one I deleted. So now we have these cells that we just grabbed from the other one. So I don't have to write this first cell. Okay, I can run it. I already have these. I can run it. But now we're looking at external data, right? And you'll see that it has that processed and that raw folders, and within those it has the CSV that it just created, and we have the checkpoints because we opened them here in JupyterLab. So first things, we can create a data frame, PD, read, CSV, external. I'm gonna use the slash again, this is how I prefer it. We're gonna go into another folder, processed, within it. So we're gonna do another slash, and we're gonna do ACS5_2018 race counties.csv, and we're gonna do data.head, and like we did before, I'm just gonna transpose it right away just so you can see it in a much more legible manner. And boom, we got the geo ID, we got the name, we got the universe for each of them, the annotation, the universe margin of error, and all these columns. And just like in institutions, we have, this is what would be a master file. This is something that we just got. This works for what it exists for, but that's not exactly what we want for this project. So we're going to create a subset from this for this project at hand. This is going to be our working file, our analytical file. Okay, so just like we did before, we're going to create a variables of interest list. But you may have seen that what we're interested in is these /_alone columns, right? We want universe and we want alone. So what we're gonna do is, instead of typing all of those by hand, we can do a list comprehension. This might be a little advanced to beginners, but these are really cool, and I think it would be useful to go over it. It's kind of simple in a sense, and it's good practice. So this is how we're gonna do this. So we're gonna grab the column for column in data.columns. Actually, let's write it from. If you click on a cell on the outside and you click the key B, it creates a cell below the one you have selected. So if we do this, call in data.columns, it returns everything, right? Because so we're saying it's a list comprehension. We're saying, okay, grab a call, or this could be anything, right? For each element in this other thing. So grab the column for each column in the data.columns. And what we want to do is, okay, we have all these, but this is not what we want. What we want is the ones that don't say MOE, because we don't want the margin of error, and the ones that don't say annotation, because we don't need that. And you may have noticed, actually, at first we thought, okay, we can do just _alone, and then just get rid of this, the one that says annotation and the one that says MOE. But universe doesn't have _alone, and name doesn't have it, and GOD doesn't have it. So a better way to filter out the columns that we don't want is by not including them in this list comprehension. Instead of grabbing the ones that just say _alone, let's just get rid of the ones that we don't want. So let's do an if statement. So if MOE is not in call. Boom. So we got rid of all the ones that don't have. If there's an MOE inside the call string, I don't want it. Drop it. So that's the first filter we're gonna do. And we don't want annotation either, right? So and annotation not in call. See? Boom. This is exactly what we wanted, right? We have GOD, we have name, universe, all the white, black, American, Indian, Alaska Native, Asian, Native Hawaiian, Pacific Islander, other, to Latino. All of those that are alone, we got those. And we also have state, county, Asians, all, other, all. So this is the list comprehension we want. We're going to do Command C. And we're going to copy and paste it over here. That's our list of variables of interest. Just like we did the other one. Now we're going to create a working data frame. Working data. It can be working, you can call it whatever you want. I call it working data or working DF. It depends on absolutely nothing. It's just completely random. That should be more standardized when more. Dot copy, because like we mentioned before, we want a copy of that data frame. We don't want kind of like a window into it. We run that. Let's make sure that it's working. Dot head. Boom. This is what we got. This is what we wanted. Okay. Now that we have created this subset, we can save it. This is what we wanted. I'm going to click the escape key. I'm going to click the M key. So this is now a markdown file. A markdown cell. Pound, not hashtag, pound. Checkpoint. And we're going to save it. Working data to CSV. This one's going to be on processed / counties.csv. Again, we don't want the index. False. And encoding. This one is kind of redundant. I'm pretty sure these are fine. Coding UTF-8. Run. Cool. That's ready to go. And we can check in our process data. Now we have the county CSV and the institutions data CSV. Right? So now we have these. And we can start answering our research questions. Awesome. Notebooks. I'm going to create notebooks. Let's call this research question 1. This is where the fun starts. We're going to use this. I'm going to show you how to do it the other way. I'm going to call this, I'm going to make this a markdown file. Research question 1. How many higher education institutions are found in cities, counties, not cities, with majority underrepresented groups? And then we have a sub research question. What are the characteristics of those institutions? Right? Do they vary? Are they the same? What's going on? Let's run this. Okay, so first we're gonna do the same thing. Import pandas SPD. This one I'm gonna do from scratch instead of copying it from the other ones, because we're gonna import some new ones. We're gonna import GeoPandas as GPD. We're gonna import GeoPlot as GPLT. This is gonna get confusing, so make sure that you type it right. Especially GPD. I usually do GDP, but that's because social science. Import GeoPlot.crs as GCRS, and this is the CRS in GIS is the coordinate reference systems, right? And this is about projections. This is what tells us, and it tells people how to display the coordinates in the shape files onto a 2-dimensional plane, right? So you've seen those. You've seen the way if you have certain type of projections, Greenland looks huge, and then if you see it on the globe, it's not as big. Those are different types of projections. We're not gonna go too deep into this, but that's what it is, and we're importing it because GeoPlot provides an easy way to change projections without you having to do all the math. We're gonna import matplotlib.pyplot as PLT because we wanna do anything with the figures, add titles, etc. And we're gonna do pathlib, of course. For pathlib, import path. From datetime, import datetime as DT. And I recommend doing the as DT because it can get confusing when you import datetime from datetime. But you can do whatever you want, of course. DT, we're using today. SDRF time, we're doing the day, we're doing the month with the name, with the letters, the 3 letters. I'm doing only 2 of the year. And we're running today to make sure that we got it. Yay! And if you're running this locally, of course, if you're creating the environment, it should work. If you're running this on Binder, it obviously is working. If it doesn't run locally for some reason, I would just jump on my Binder. And if you were trying to run this locally and then you run it and you run into an issue now, I would just go on my binder and then run the first two, the data prep counties and the data prep solutions data prep institutions from the solutions folder, so you can get up to speed. Working with geographical data and installing GeoPlot, GeoPandas, they have a lot of dependencies and that sometimes don't play nice locally. They've been getting a lot better. Shout out to the people in Conda Forge that have been making this really great. It's just way easier to work with these from what I remember when I first started, and from what I hear of people that started way before me. Okay, so I open up this one because I want to be lazy and copy just these paths so I don't have to write them. I'm gonna cut this one out. And yeah, that's pretty much it. We're gonna do tree on processed data because that's where we just saved everything. Forgot to import from tools, import tree. Yeah. Okay, so like we mentioned, you have the checkpoints. We can ignore those. The geo data is here. These are the shape files. We have our county CSV that we just created on the data prep counties notebook. We have the institutions data CSV from the data prep institutions notebook. And what we want is to grab the shape files, the institution data files, and then county level data file, read them all into data frames or geo data frames, and play around with all of those. So counties, institutions, shape files. Counties and institutions are CSV files. So this is how it works. Counties, we're going to call it counties data because we also have the shape files for the counties. So it's counties shape. Counties data, PD, read, CSV, processed data. I do tab autocomplete to make sure that I don't have any typos, which usually happens. Process data, we're gonna do counties.csv. We're gonna do institutions data equals PD, read, CSV, process, tab, institutions data.csv, and county shapes. This one's not going to be PD because it's not pandas, it's GPD, and it's not read CSV, it's read file. And you can do read and then do tab to see what are the options. You could read a CSV file on PostGIS. What I do is read file for this, what's going on here in the geodata folder. It's going to be processed data dot geodata because that's the subfolder it's in, and TL 2019 US county dot shape. That's the file that we want. And GeoPandas is smart enough to know that when you point to the .shp file, that it's in a folder with the DBF, the CPG, the PRJ, points with everything. So you just gotta point to that one, and it's gonna read it all. And we're gonna run this. Yay! Okay, so let's counties data. This is a transpose. So this is what we just did. Institutions data. Same, this is what you just did. And now let's look at counties shape. Oh my god. I'm gonna change this. Doesn't really matter, I could have just gone with county shapes, but for consistency, counties shapes dot head, and I'm gonna do T to transpose it from the beginning. And you'll see that we have state FIPS code, county FIPS code, GeoID name, a lot of information for each county, area of land, area of water, and this is what we want, geometry. This is what GeoPandas brings into the pandas ecosystem. It adds the ability to have a geometry series, a geo series that can hold polygons, multi-line strings, points, and it just knows what to do with that. So if we do, for example, institutions data.plot, it's going to be super ugly. It just, pandas knows that you want to plot something, right? It doesn't know what, so it just adds all the variables. But if we do counties shapes plot, this is GeoPandas, and it knows that you're working with geographical data. This might take a while because it's big. Oh, it knows that you're trying to build these, to map these, to illustrate your polygons, right? So what we want is, you'll see that we have Alaska, Hawaii, Puerto Rico. We have everything, right? For simplicity purposes, we're only gonna focus on the lower 48. Apologies to everyone outside that. It's just to make the math more concise for this workshop, but you don't have to. But this is what I'm gonna do. And also, to illustrate this really cool package called us, import us or US. And you can find that on PyPI. Us. It's pretty cool. It's a package that it helps you work with US and US state metadata. It has all the states and territories, the postal abbreviations, FIP codes, capitals, years of statehood, time zones. It's just really cool. We're not gonna go too deep into this, but it's very useful. Anytime you're working with census data, every time you're working with geographical data in the US, this is really useful. So what we want is US state contiguous, and this returns all the states, the contiguous United States. And what we want is, we're gonna create, let's grab the first one so you can see what it is. So we have state Alabama, but this is not a string. This is a state class, so you can access its attributes. State FIPS, state name, Alabama, yeah, state abbreviation, I think, yeah. Okay, so what we want is the FIPS codes of the states in the contiguous United States. So what we want, we're gonna grab the FIPS for each of the states in the contiguous United States, and just like we did before, we can do that by starting a list computation. We're gonna have grab the state for state in US contiguous. It returns all the states just like we did before, but what we want is the FIPS of each of those states, right? Voila. Okay, so contiguous FIPS, and what we want is create what's called a mask contiguous FIPS, which is what we're gonna use to filter out the shapes that are not in the contiguous United States. Contiguous shapes. Oh, sorry. Count these shapes. So grab that state of P is in contiguous FIPS. So this is saying, grab the state FP column of the county shapes data frame and check each of those elements if each of those elements is in the list contiguous FIPS, and that's going to return true or false. Let's see, for each of those elements, right? True, blah blah. So what we can do is use this to filter out all the falses. So when you pass pandas a list of trues and falses attached with the index, it's going to tell you whether or not it tells pandas whether or not you want to see that in your data frame. So this is a way to filter out any rows that don't match any of these conditions, and this is where you create the mask. So what we're going to do is overwrite this counties shapes. So now it's only contiguous counties. And we're going to want to do the same thing for the institutions data, but our institutions data is not using FIPS code. It has FIPS code here, but it's using state names. So what we want to create, we could do US has this, no, is it mapping states mapping. It has the capability to return, yeah. So we want name to FIPS, and it creates a dictionary that we can use to map into a panda series and create and transform state names into state FIPS codes. So we could do that and then reuse contiguous FIPS. And actually, let's try that because it's good practice. Let's see. We're gonna use this. We're gonna name it name to FIPS map. And the way you do that is institutions data. We grab a series, is the FIPS state code, and you map the new set of values. And we pass it this dictionary named FIPS map, and what? It changes all those names into their corresponding FIPS code. And we can rewrite that same series, call it institutions data, square bracket, FIPS state code, institutions. And now if you look at institutions data, FIPS code, we change it to this. So we can now use mask contiguous FIPS institutions because they have different indices, which is it's also important here in pandas. You could not use the same mask because this mask is not a list of values. It's this trues and falses, but it's a panda series, and it's attached to this to an index, and the index is important. So we're gonna create a new mask contiguous FIPS institutions equals institutions data FIPS state code. We gotta make sure that is in contiguous FIPS, and then we overwrite institutions data mask contiguous institutions. You run it and you see 3,700. So we dropped a few. See if you remember how many do we have? Institutions data. One way to check the shape of your data frame, the number of rows and columns, is run shape. It's not a function, so you don't do the parentheses at the end. So we used to have 3,751, but with this new mask, we only have 3,714. So we dropped a few that were outside of the contiguous United States. So that's already an equity issue, right? I don't know how many people are outside the contiguous states, and there's only 37 institutions outside the contiguous states. So it's already a policy question that you could ask. institutions data equals the mask. So we're dropping all of those institutions outside. Okay, so now we have this. I'll preview that. So we have our working data. We have the shapes and the counties and the institutions. But the question is, how many higher education institutions are in the counties where there's a majority of underrepresented groups? So we need to define what's majority underrepresented groups, right? And one way to do that is with this counties data. That's how we're gonna find out which counties are majority underrepresented. So the way to do that is we're gonna create a new column, counties data share underrepresented, and that's gonna equal, I'm gonna open a parenthesis because it's gonna be a bunch of stuff, a bunch of other columns, counties data black alone plus counties data Latino alone plus counties data American Indian and Alaska Natives, counties data Native Hawaiian, and actually you can break it down a little bit more just to make sure that it works. If you're running this in a parentheses, it's just gonna work, so you don't have to worry about the indentation. Okay, so we have Black, Latino, American Indian, and Native Hawaiian, and I mean you can include two or more races or other, but these are the major groups of historically underrepresented people in higher education. So we're gonna add all those up and we're gonna divide it by counties data universe, which is all the people in that county. Let's see if this works. Voila. I have counties data. Let's see. Let's transpose it. So we have created a share underrepresented, and this is 0 to 1. This is a percentage of people of underrepresented backgrounds for these four racial and ethnic backgrounds in that county. So Barber County, Alabama, 52% underrepresented in the higher education system, historically underrepresented in the higher education system. Baldwin County, Alabama, 15%. Blount County, 11%. So even around here, you already start seeing some variation, which is always interesting in the research context. So now we have the column that we're gonna use to see or to answer our question. So we're gonna use, just like we did the working files for the other, for our earlier stuff, we're gonna create a subset of, even a smaller subset of each of the data frames that we're working on, because now that we have this, we only want really GeoID to match them, the name, maybe university if we want, but it's mostly share underrepresented. That's what we're after, right? So we're gonna create subset counties data, and it's gonna be counties data, and we're gonna pass it our variables of interest, GeoID, we want name, and we want share underrepresented. That's one thing we want. And we want to copy it again. We're gonna do the same for our shapes, because we don't want just everything. We don't care about, for example, the area that's land and the area that's water for each county, right? You might be interested in that. That might be another question. Are there less institutions? Are there less higher education institutions in counties without water? Counties, shapes. So we're gonna do counties shapes. We're gonna pass a subset of variables of interest. GeoID. We also want the name and the geometry. We want a copy. And this is something that you may not have noticed right away, but if you've been working it with census data before, if you know FIPS codes and GeoID codes, you would know that it's 5 digits. It's 2 digits for the state, and Alabama is 01, and 3 digits for the county. So it should be a total of 5 digits. The problem here is that subset counties data D types, that's how you check these. Our GeoID is coded as an integer. So the first 0 is not, it doesn't matter if you're working with actual numbers, but these are codes. So we need to change this first into a string and then add the zeros on the left. And the way we do that is by using the zfill attribute, the zfill method on this string. So subsets. So how do you grab a series, a column from a geodata frame, from a data frame? Square brackets. We're gonna grab GeoID. So this is what we have. You can also see here that the type's int 64. So what we want is first transform it to a string. So we're gonna cast string as the type for GeoID. We run it. Now it's the type object, which is how pandas calls anything that's not an integer or float or boolean, I think. In pandas 1.0 now you have a string d type, but that's not what we want right now. So as type, I mean, it doesn't matter, but not important. So the way we apply string methods to a series, just like we did earlier, is by the string accessor, right? We're gonna do str, and then we can actually call string methods onto it. Zfill, and we're gonna do 5 because we want 5 for it to fill up to 5. Voila. Now you have this 0 before, which is important because in our county shapes, it actually, oh, you can't see here. Let me see. Counties shapes. Let's do a sample of 5. If you do sample, it'll grab 5 random. Sample, it grabs at least 1, but you can specify 5. It's gonna grab 5 random rows instead of the first 5 if you do head. Oh, perfect. You see that here, Grant County is 08049. So GeoID here does have that 0 at the beginning, and for us to join the data onto the shape, we need them to match. That's what we need to do all of this. We need to add the zeros here. Now that we know that this works, we're just gonna overwrite that series. Subset counties data GeoID equals bam. Okay, the way to do this now, because we're gonna join them, is we're gonna do subset county data set index counties. We want the GeoID to be the index, right? To make sure that these are unique, and to make sure that when we join them, we're just gonna join on the index to make sure that the data frames know that that's what we want. Subset counties data, so geo index, and we can do just like we did earlier, subset counties data equals that, because it's returning that same data frame, so we're just gonna overwrite it. Are we gonna do the same with subset counties shapes equals subset counties shapes set index GeoID. Bam. And let's join them. Now what we want is, we have the statistics, we have the demographics and one data frame, the county's data frame, and we have the shapes onto another data frame. And what we want is to be able to match those. So we know this shape has these characteristics. This county over here has X share of underrepresented people, and that is the same. So when we create the maps, we can say, okay, this is the shape, color it based on this column, on their share underrepresented attribute, right? So we're gonna join them by saying subset counties shapes join. We're gonna join the subset counties data. Let's see if this works. Perfect. And this is doing the matching automatically on the index. That's why we make sure that we set the indices to be GeoID and not the 0, 1, which meant nothing. The values didn't add any information to it. Okay, so now we have each of these has a name from the geodata frame and a name from the county's data, which we got from the census, both from the census, but this is from the census data downloader. And you can see I included the name. We didn't have to include names, but I included the name as a way for us to check and make sure that we didn't do something wrong right away, right? So we see Gilmer, and we have Gilmer County, Georgia. We have Rousseau County, Georgia. So it's a quick reality check on our data. And we're gonna call this working GDF for working geodata frame, right? And you don't need to do the copy because it's a brand new data frame. Alrighty, so now we have this. Let's see how we're looking. Let's do plot. I'm adding the semicolon because watch. If you don't do a semicolon, you get this, which is kind of ugly. Just one way to keep things a little bit cleaner. So this is the default illustration for geodata frames, and I think we can do column equals share underrepresented, right? And we can start looking at how things how the country looks in terms of underrepresented people, historically underrepresented people in the higher education system in the United States seem to be around the South, Texas here by the border, and these areas over here, which makes sense because this kind of looks how just a general population distribution would look like. These are the centers where there's more people in the United States. But this is why we included GeoPlot. GeoPlot makes things prettier by default. So what we're gonna do is use GPLT, GeoPlot, and do this is what's called a choropleth. And we're gonna pass, let's see, Shift Tab. The DF is gonna be working GDF. The projection is gonna be GCRS, and real geographers are gonna hate me. I went to NCES last year, Mercator, the North American Conference for Information. No, the North American Cartographic Information Society. Their conference last year, I presented on how to make maps with Python. And right before my presentation, I went to the poster session, and there was this little area where you could leave post-it notes for other people to see. Tips, tricks, whatever you felt like sharing. And these are anonymous, and someone wrote, do not use WebMercator, or stop using WebMercator. And I had, in my presentation that I was going to do later that day, all the examples I was using was WebMercator. And it just works, especially when you're looking at one country, the US specifically, it just works. So it's fine. This one takes it a little bit longer, but you'll see the difference. So this is the default in Matplotlib. It's already great, right? Like you can still see the information. If you don't know Matplotlib, you might have to maybe Google oh, how do I get rid of the axes? How do I add a title? Blah blah blah. But with GPLT choropleth, it just kind of works. It's pretty nice. Okay, while this is working, while this is going on, let's do let's start working on our institutions, right? So we have a data frame with our institutions data right here, and it has a longitude and a latitude. This is still a tabular data. This is still from a CSV, but longitude and latitude are characteristics of a geography, of a point. There's the X and the Y. And what we want is to change this from a regular pandas data frame into a geo data frame and create that geometry column. And it's the only difference is that instead of polygon, what we want are points. And these points are going to come from longitude and latitude. So let's see how we do that. We're going to do GPD, geo data frame. We're going to pass it the institutions data. We're going to do geometry equals GPD. And we're going to call the function point from X, XY. That's what it's called. And we're going to pass it the series institutions data longitude and institutions data latitude. Just check that. Notes. That's what it is. Oh, and look, GPLT, geoplot. It worked. Again, looks pretty much the same, but it's slightly nicer. The default figure size is a little bit bigger. There's no axes, but the colors are the same. The lines are the same. So I prefer to use geoplot because I when things are slightly better to look at right from the top, it's just less cognitive work that I have to do, right? Like I don't have to zoom in and I don't have to ignore the axis. It just goes in. It's pretty nice. So let's try this. We're creating a geodata frame from the institution's data, and we're saying create the geometry column from these points, from the longitude and latitude. Let's run this. What? Oh, sorry, I'm checking my ass. Oh, dirt. It's points. And voila. Now we have this, and now it has this geometry column, and you can see that it's 8-point geometry. So let's just work it. Let's just save it as geo institutions. And remember when I mentioned that there's CRS, the coordinate system? So let's see. You'll notice that the working GDF CRS, the coordinate system for this one, it's set up. It comes from the data. That's what one of those multiple files from the shape files. This information comes from there, and it tells you a lot about about how to display this information, this geographical information. And if we do that for our geo institutions, it doesn't have anything because we just created from longitude and latitude, but we didn't specify the bounds. We didn't specify what, if it's using degrees or if it's using meters, etc., etc. But we do know that it's using degrees because we can see it here, right? This is not like 180 meters from whatever point. So what we can do is just copy that from the other one. And now it just works. And this is gonna save you some warnings later on in the process. It's just, might as well get it in from right now. And what you can do is, let's do GPLT, a point plot using geo institutions. Let's see if it works. Okay, so we can see these are all the institutions in the country, right? Obviously this doesn't tell us a lot. what we want is maybe a way to combine this one with this one right here. So we can see how many institutions are found in counties with majority underrepresented groups and what characteristics are those institutions. So we can do first visually, throw it on top of it and then see like, oh, is the majority here, which I would assume this is probably the most populated areas in the United States and the little centers here. So I would expect that the institutions are mostly like around here, but you can see here that there's a lot going on here too, right? But we don't want to go between two maps. So what we're gonna do is create an axis. We're gonna do GPLT core path. We're gonna copy this one. This is what we're gonna be doing. Except it's not the last one, so this is not one. So what we're gonna do is fixed size equals 1212 because we just want it a little bit bigger. And we're gonna save this to an axis. So what we want is to create, first make me a map and then throw the other one on top of it, right? We don't want two maps, we want them one on top of each other. So we're gonna do x equals this. And then on the point plot, we're gonna specify that we want it on that same axis, on that same chart. What we're gonna do is GPLT dot point plot, just like we did right now, institutions, except we're gonna specify that it's on that same chart. We're gonna do Z order, so specify that we want it on top of everything else. We don't want to just cover everything, so we're gonna make the circles a little bit transparent. 0.3, and we're gonna do color red just to make it a little bit easier to read because this is blue on blue. And we're gonna make the size 2, right? And all this comes from me having worked with Matplotlib before and constant Googling, because if you do Shift Tab, you're gonna get some of these arguments that you can pass, but color and size and alpha and Z order, those come from these keyword arguments that they pass to Matplotlib behind the scenes. So you don't have to, they're not gonna show up right away. You're gonna have to Google and you have to work with Matplotlib before to know this. So we're gonna see this. Let's see if this works. Let's see how fast this works, because we noticed that. Oh, interesting. We noticed that. You notice that this took a bit, right? This was kind of slow. Let's see how long that takes. And in the meantime, my mistake. Color. Where did I put 3? Did I say red? It's red. We want the red. That was faster though. Did you notice? There you go. So this doesn't answer the questions. It doesn't answer the question directly. Like, we still don't know what this county is, right? Or this county here. Well, we started to see something. We started to see that even though this might be this whole area is populated in the United States, but the majority on the representative groups are around the whole south of the United States, and these centers over here at the very top and here. But the higher education institutions are like equally distributed around this half of the United States. So even these are mostly white and Asian populations, mostly white, and there's a lot of higher education institutions around here. So we're starting to see some answers, and we're starting to think we can start to use this as inspiration to start thinking about the equity implications of where these institutions are. It's not like we can fix everything right away. It's not like you can just create a university and in like 6 months be like, okay, we're just gonna throw all these universities in the south. but visually you're starting to see something. Okay, now let's do, what we want to know is, just like we filter out the counties before with that were not in the contiguous United States, we can do the same thing, but the filter now is gonna be that 50% threshold. Does your county have 50% or more underrepresented groups as its population? So we're gonna create a mask for pandas, mask majority underrepresented equals working GDF, just share underrepresented, tab autocomplete, so I don't make any mistakes, and check whether or not this is over 50%, so 0.50, right? And we can do, so that's the mask. We can do a quick plot of working GDF. We pass this mask maturity. Oh my god, represented. So these are this is already including that mask. So you see there's only 294 counties with majority underrepresented populations. We can do the plot. And these are it, right? And it makes sense. You see the brighter colors here. And the way pandas works, and Python in general, if you pass the spiggle line, that's the negative, right? That turns true into false and false into true. So you run this, and you should get the opposite, right? So now you're saying you're negating this. So check for counties where the underrepresented, that is not true, that the share of underrepresented people in that county is over 50%. And that means we can do this. Majority underrepresented equals working GDF mask 100%. That copy. And what we can do is, let's see this. So these are the counties, and we want to know is this institution in this county? Yes or no? Let's find the institutions that are found within this county, and this is the first round of geospatial components into this, right? We could do some string matching and see, okay, well, what's a county this institution is and what's the state, and we can create something like this and then try to match it on that. But if you know GIS, you can just check, is this point inside this area? That's how we do it in real life. Like, is this point in this map here, is it inside or is it not inside? So that's what we're gonna do with GeoPandas, and what that's called is GeoPandas. Instead of join, we're gonna do S join. It's a spatial join, and we're gonna check geo institutions in the majority underrepresented. How are we gonna do it? We're gonna do an inner join, so only institutions that appear in both data sets, in both data frames. And how the operation that you're gonna be doing is check whether or not this point and this polygon intersect. Section intersect. And let's run this. Okay, so what this is doing is grab the information, do an inner join where they match. And how are you checking what's a match? Is check if this point and this polygon intersect. That means this polygon overlaps the point, or this point is inside the polygon, right? That's what the intersection means. And okay, so we have this, and we could just assume that it did it right. But here's the cool thing about GeoPandas. Plot. Okay, so now you have the institutions because the geometry is the points, and now you're only checking for points that appear within those polygons that we have chosen to be only the polygons of the counties where it's a majority underrepresented students. And you can see this matches this more or less, right? So now that we have that, we can save that as institutions in majority underrepresented. We're just gonna call that it. We don't have to go too much. And we don't want the plot, we want the data frame. Saved. And what we could do is recreate this, copy, paste, and instead of this, we're gonna do institutions in majority underrepresented. Bam. Let's see how that looks. And these are just reality checks. You're checking that what you're doing matches the reality. You're looking at a map, you're saying, I want to look at the institutions in the counties where I said they're majority underrepresented. If I plot them, do they show up in those counties? And it looks like it does. Look. Cool. All right. I'm just gonna say that real quick. But the real answer is not a map. If this is a report that you're presenting, you're not looking. You can't just throw on a map and be like, here it is, right? I want to know the statistics. What are these institutions like? So let's see, majority underrepresented shape. It seems like the majority underrepresented counties, like we said, is 294 counties out of 3,107 in the contiguous United States. Geo institutions, it's all the institutions in the contiguous United States. That's 3,714. But institutions in majority underrepresented, it's only 659. So that's already like a fifth of the institutions. So let's see. Let's do some pandas data analysis real quick. We're gonna grab these institutions in majority underrepresented. Let's see what information we have. So we have the name, latitude, latitude, FIPS, we don't want that. Total enrollment, part-time, full-time, control, level. These are interesting. Are they mostly private nonprofits? Private for-profits? Are they mostly public? Are they mostly 2-year or 4-year? Let's see. Let's look at institutions, majority underrepresented. And these options show up if you click tab, by the way. Let's look at sector. Sector. Value counts. Oh, it's not sector. We got rid of that. It's control. Okay, so we have out of the 659, 257 of them are public institutions, so that's nice. One thing to do here is like these are the counts, right? So this tells us something. It's mostly public, and then it's mostly private, not for profit. One way to look at this, we can pass that normalize equals true, that argument, so we can see the shares. So 39% of the institutions in the majority in counties that are 50% or more underrepresented groups are public institutions, and 32% of them are private for not-for-profit, 29% are private for-profit. So that tells us something, right? We see that still mostly public institutions, but how about in general? Well, how about all the institutions? How do the institutions that are in these counties compare to the total, to the rest of the institutions, to the whole universe of institutions in the contiguous United States. So let's do value counts normalized equals true. And you can see the differences now. You can see that in the whole contiguous United States, 43% of the institutions are public, compared to 39 in the counties where it's majority underrepresented. That's not too big of a deal. I mean, 3%, still around 40%, right? Private not-for-profit, it goes from 38% to 32%. So that's a bigger gap. That's 6 percentage points. This is what's interesting. In counties where there's a majority of underrepresented groups, of historically underrepresented groups in higher education, there are 29% of the institutions in those counties are private for-profits, as compared to only 19% of the institutions across the contiguous United States. So that's a 10% difference. So now we know something. Let's do markdown. In counties where there's a majority of underrepresented groups, and the language can get a little bit confusing. So counties where there's a majority of underrepresented groups, 29% of higher education institutions are private for-profits, whereas across the United States, that number drops to 19%. So there's that 20%. That's the answer. That's one of the answers, right? How many higher institutions are found in this? Blah, blah. We already answered this. We have only 659. What are the characteristics of the institutions? More private for-profit. That's one of the answers. Let's see if this varies between the 2 and the 4 year. So let's see institutions, the majority underrepresented. Let's look at level, value counts, normalized equals true. And let's do the same for our geo institutions. Oh, that's interesting. Now, institutions in majority underrepresented counties with 50% or more underrepresented, historically underrepresented groups, 58% of those institutions are 4 years or above. 42% of them are 2-year institutions, whereas in the United States across the country, 64% of the institutions are 4 years or above, and only 36% of them are 2-year institutions. So the institutions in the majority underrepresented are more 2-year than across the United States. There's 4 year. Oh, that's interesting. So that's research question 1. We can also look at total enrollment. We can look at part-time versus part-time versus full-time shares, and I leave that up to you. You should pause the video right now and run through other statistics that you might find interesting and set them up. put them up over here. And once you've done with this one notebook, what I would recommend is doing file, download, and then just saving it for your own, because this is in my binder, so it's ephemeral. It just kind of goes away after you're done with it. And I would do the same with the data prep notebook. Download this one too. Download. And now you have them locally for next time you. So if your my binder instance dies, or you didn't run code for like more than 10 minutes, it will die, and then you're gonna have to refresh, and it's gonna spin up a brand new environment for you. But if you download these, you can drop them, you can upload them here. You can do upload, and then it just works. All right, let's move on to research question number 2. Hey everyone, we'll get started with research question number 2. You may notice the change of tire. I'm recording this on a different date, and this is a perfect opportunity to show you how you would jump back into the workshop after doing steps 1, 2, 3, and then you wanna jump all the intro stuff and go back to research question 2 or 3, right? Which I assume you would do if you don't want to sit down and do the whole workshop in one sitting. If you wanna, if you do like the first part and then you don't want to sit down for 2 hours, you step away and you only have 15 minutes for my binder for the instance to go away. You just download your notebooks just like I did before. You go to the GitHub repository, click on the badge again, and you'll notice that it should be that the image is already built, so it shouldn't take too long. But if it's not built, like I mentioned earlier, it's gonna build an image and then it's gonna take a few more minutes. And all you gotta do really is upload the notebooks the work that you've already done. So we'll go to notebooks. You can also go to solutions and then just run the data prep counties and the data prep institutions notebook, and then research question 1, 2, 3, whatever you did, right? To kind of catch up to what you were doing. What you can do here is click on this button to upload any notebooks that you have already. What I'm gonna do is drag and drop my notebooks into that area. I have research question 1. I have data prep institutions, and I have data prep counties. And we'll start with institutions. Since we already know what it is, like we wrote this code earlier, right? So we know that it works, and we know it ran perfectly. So we can just run all cells, and it's gonna create our institution's data CSV. Another way to do this is, and let's do it with counties. Another way to do this is go over here on this button in the drop down menu, run all cells. And if we do this right now, you'll notice that this is from our last session. This is tree on external data, and you'll notice that we have the zip file that's included, the counties shape files, but there's also this these 2 folders, processed and raw, which is data that we got from the census data downloader tool. So if I run this, run all cells, I'm gonna get an error. You see, in external data, we only have those included files, the files that I included earlier, and this is gonna give us an error because there's no ACS 5 2018 Race County CSV, because that's the one we got using census data downloader, remember? So what we're gonna do is have to run it again. We're gonna change directories CD into the data external. You could also do census data downloader data there, and then provide like data external, right? But I just to save us the long command, I'm gonna go straight from here. Because it's a brand new instance, we still need to export our census API key. We need to export it again. Command C. Yeah, we're gonna need this anymore. Okay, so that should work. Now we do census data downloader, specify year. You might not have to because it defaults to the latest year, 2018. Census data, we asked for race, counties, right? Enter. Takes a little bit, and then it just downloads every single one, every table for every county, remember? Come on. There you go. The Jupyter Lab interface also sometimes takes a little bit to catch up to what's actually in there. It's not refreshing constantly. You may notice when I uploaded the notebooks, you can drop it and you're not gonna see it right away. You can go over here and refresh it, and then it's gonna appear. It's just that the interface is not updated constantly. Okay, well, now that this is working, let's see if we can load it. Perfect. Checkpoint. Save. So now we have the county's data and the institution's data, and we can run this. Let's see if it's working. Oh, everything's running smoothly. Let's see if we can. These two will take a while. So let's just, oh, that was fast. If we run everything, it should all work, right? Oh, the core plot from GeoPlot is what takes a while the first time. I don't remember exactly why. I wonder if it's downloading anything for the CRS, the coordinate system. Okay, so we just did this, so I'm not gonna go over this. This is just rerunning all the code, because what I want to show you is we have a working GDF. That's a GeoDataFrame. This is something we didn't do at the end of the last section when we finished our Q1. We have a working GDF that has where did we make it? Subset of county shapes, subset of counties data. So this is the contiguous United States, right? And it has the shape files and the data attached to those shapes. That is this data, the share underrepresented, and the name and the GeoID. So this working GDF is what we really want for the rest of our analysis, right? So we're gonna create an analytical file for the shapes too. We're gonna save this GeoDataFrame, so we don't have to load the shapes, load the county data, merge it, and apply do whatever else we needed to do. This is just gonna save us a couple steps, and it makes it more reproducible, because then anything I do if I need to change the underlying data set, if I don't want to look at just the contiguous United States, I just come over here and change it in the first RQ1 and be like, okay, well, I want all the research questions to be about the same data. So I modify it in one, and this one question is saving it. So all the following analyses are going to have the same data. Instead of in each research question loading a data shape file, loading the data, doing the merging work, and then having to update that in every single notebook. All right, so it seems like everything is working. Oh, another core plot. See, this is way faster. I think it is. I think it is that it's downloading something. I'm not sure. Everything's looking good. Okay, so we're gonna do just like we did in the other ones. I'm gonna switch this to markdown, and then checkpoint. I just call them checkpoints, but it's just saving your data, right? As the last step. So what we have is the working GDF. Let's see what data it has. It has a name, it has the geometry, it has this, just like a reality check. This name comes from the census data downloader data, and the share underrepresented. We also have geo institutions, which is essentially the same data set, but with a geometry attached to it. It's the institutions data set, but a geometry attached to it, right? So what we want to do is just save these as geo data. So we want to save it as those shaped files that we already did earlier in this question, especially because, as you remember, we added the CRS to our geo institutions, right? So we're already attaching some extra metadata to it. And I mean, we can, again, it's just saving us some steps. So the way to do this is working GDF to, there's the tab, it's a geo data frame, but it's giving me a bunch of pandas data frame options. Okay, just so we don't make a mistake right now. Another lesson, GeoPandas, saving files. GeoPandas.org, they have some pretty good docs. So it's because we do read file, that's how you read something. But then writing to file, yeah, see, and it didn't come up. And you can use different drivers, so you can save it as a GeoJSON or as a shapes file, which is really useful, especially if you're going to be working in the web and you want to create a map with something else like D3 or go to like data wrapper. You can upload your own GeoJSONs and just have all this data attached to it. It's really good. So first things, we're gonna do process data. Let's do what's in there, right? So we have a geodata folder, we have the county CSV, the institutions data, and the process data. What we're going to do is, using pathlib, using this path, we're going to do process data join path. We're going to create a directory for this working geodata. We can do processed geodata dot make dir. Okay, and if we do, we're gonna do the same processed data dot join tab, so it's autocomplete. Processed institutions. Then make dirt. Run. And I know how people hate that you go back up a cell and you ruin the flow. I was like, oh, it's not reproducible. Okay, so we're just gonna do it over here again, just to show the difference between two. Now you can see that we have another two folders: process geodata and process institutions. And you can also check it over here if you want. Processed, right? It created those directories. So working GDF, we're gonna go to file, and we're gonna do process data, processed geodata, and we're gonna name it, we're just gonna contiguous US. Dot shape. It's gonna run. And we're gonna do the same for geo institutions. To file, process data, process institutions, geo institutions. And the way I created, the reason why I created these directories is because shape files are not one file, and just to keep things neat, when you save something to that SHP file, it creates all these complementary files that go with it. And we could have all this here and then just have like 15. And it's like the same reason why we have this. It's like if we had like 15 shape files over here, and then 5 of them, each group of 5 had the same name except just different ending, that'd be too much. Okay, now that we have saved our data, we can move on to research question 2. And it's gonna save us a lot of time because we already did most of the work of the data preparation over here, right? We don't need to merge all this data, clean it up. So we're gonna go notebook. First things first, you gotta rename it. You don't want untitled number 17, right? And we're gonna be a little bit lazy and just copy the first 3 cells, right? Oh, actually, yeah, not the first one. But we don't need this one. And this one, I'm just gonna leave. Oh my God. Perfect. So it's not research question 2. I mean, research question 1 is research question 2. Research question 2, are there any, actually let me delete this too. Sorry. Are there any counties, I'm checking my notes, so that's why I'm looking this way, that don't have any higher education, institutions, aka education deserts? Oh. What are the demographic characteristics of those counties? Okay, and then we're gonna be importing GeoPandas, GeoPlot, Matplotlib, tools, pathlib, datetime. We're doing the same thing, the same work, right? And then we're setting up our paths to our data folders. We're looking at process data, and you'll see that now you have these, right? We have your folder with the process geodata and the process institutions, and now we can do we'll just call it counties. Actually, no, because that's gonna get confusing. Let's call it contiguous United States. So it reminds us that it's not all of the US. Read file. And afterwards, you can just go back to RQ1 and then not drop Alaska and Hawaii and Puerto Rico and all those other places, because it's also important to keep them in your analyses. It's easy to just drop things because they're a little, oh, it doesn't fit on a map, but the data work is still important, so you should include them. GPD read file processed. Tab autocomplete to make sure I don't do any typos. Processed geodata, and then contiguous US.shape, and you only gotta specify the shape one, and GeoPandas already knows that it comes with the rest of the files. And then geo institutions for consistency, read file processed institutions, geo institutions, oh, it's not that, institutions dot shape. See if it works. Okay, yeah, contiguous US dot head. Awesome. Oh, you'll notice that it fixed the column names for you. That's fine. We can change them, and Pandas allows you to have these big names and even special characters and spaces in between the columns, but when you throw it into shapefile, it doesn't work like that. So let's actually fix that right now. We can do contiguous us.columns, and then we can pass a list of the new columns. We're gonna do GeoID in lowercase because it's just easier. We can call it county name. Just call it name. Share. Underrepresented minority. And geometry. Right? And actually, just for consistency, let's do this lowercase too. Okay, geo institutions. Let's see how that's looking. Institution, longitude, latitude, FIPS state, total enrollment, full-time, part-time, control level, geometry. Well, good thing that you can still make sense of these. This is something that you need to keep track of on your own. This is 10 characters. So any variables longer than 10 characters is not gonna work. Here is GeoPandas is gonna cut off automatically. And if the first 10 characters of your variable are the same for multiple variables, then it's just gonna make this _1, _2, _3, and it's gonna be up to you to figure out what each of those mean. So just something to keep in mind. This one, I mean, it's fine. We don't need to fix any of this. We're not gonna be looking at this right now. Okay, so we're looking at counties that don't have any institutions, right? And the way we do that is by where is this? Sorry, I'm looking at my notes again. Just like we did with RQ1, when we checked if there was institutions inside a county, to check if they were in the counties where there was a majority underrepresented minorities. We're gonna do the same now the other way. We're gonna see, are there any counties? Is there any institution in this county, regardless of the county characteristics or the institution characteristics? And that again is a spatial join. GPD S join for spatial. And we're gonna do contiguous US. You do shift tab and it's gonna show you the parameters, the arguments that you can pass. The left DF is gonna be contiguous US. The right DF is gonna be geo institutions. Let's see what else. It is gonna be inner because we just want something that shows up in both. So we're checking for those that have that where there's the row appears in both because the point appears inside the polygon, right? And the operation we're gonna do is, in the last one we did intersect, and let's look at the definition they use, geometric manipulations. So they have separations and overlay. Merging data, actually, sorry. So what they have in here, spatial joints, there's 3 ways to create this operation. It's intersects, which is what we did, within, and contains. So if it intersects, is the attributes will be joined if the boundary and interior of the object intersect in any way with the boundary and or interior of another object. So if you have a polygon here and a polygon here, and their boundaries touch, that counts as an intersection, their boundaries. Or if you have a point right at the border of a county, it would still count because it's intersection, right? If you do within, the attributes will be joined if the object's boundary and interior intersect only with the interior of the other object, not its boundary on interior. So if one object is within another object, contains is attributes will be joined if the object's interior contains the boundary and interior of the other object and their boundaries do not touch at all. So within is if you have a point, let's say you have a little polygon and you have a bigger polygon, and the little polygon is right at the border and their boundaries touch. So you have the last little corner and they're sharing the lower right and the right sides of this little polygon. That's still within the bigger polygon, right? But it doesn't contain the bigger polygon doesn't contain the little polygon because their boundaries intersect. It has to be 100% inside the polygons for it to contain. This gets a little tricky. Well, this gets a little not tricky, a little confusing with points because points are one-dimensional objects. So the way we're gonna do is we're gonna do contains. Just there shouldn't be any institutions that are right at the border of a county. But if there are, we don't wanna look at those because then it gets weird. But honestly, pretty much any of these would work, especially because it's about boundaries and points are one-dimensional objects. But let's do contains because it makes sense. It kind of makes sense in your mind, like, does this county contain this institution or even within? So if we run this, let's see. So you have GeoID, the county name Lancaster in Nebraska. It has this share of underrepresented minorities. This is the geometry, the index right. So the index for this, for the institution, which is actually not relevant. The institution name, so Myotherapy Institute, Union College, Bryan College of Health and Sciences, and Purdue University Global Lincoln, and Southeast Community College area. So all of these are in Lancaster. And you'll notice that, so each of these institutions obviously has its own characteristics, but this is all the same county and the same share underrepresented, right? So we have, it's creating multiple rows for each county. And that's fine because we may have multiple institutions in one county. That makes sense. We're just gonna call this working GDF. And what we're gonna do is drop the duplicates. So we only want one row per county, and that we're actually not necessarily interested in the institutions inside those counties anymore. We're looking at the counties that have any institutions, and then we're looking at those characteristics. So we're gonna do working GDF drop, then tab to see what we can drop. Drop duplicates, shift tab is gonna show us the options. We're gonna pass this. This is what we're looking at. Subset. It's a column label or sequence of labels to consider for identifying duplicates, right? So what we don't want to look at this column to see if they are duplicates. So we could do county name, but there might be a Lancaster somewhere else in the United States, right? Or there might be Orange. I know Orange is in Florida and in California, Orange County. So we don't want to use just county name. We want to use the full name. And we can pass it just name. Let's see if this works. And you see now it's only one Lancaster per row. And this is actually not that important, so we don't need that. We can drop those later. And there's many ways to go around this. You can do other ways. This is just one of the many ways that you can do this. So we're gonna save this. We're gonna overwrite GDF. Working GDF is the unduplicated counties, and let's see. Quick sanity check. GDF.plot. If it shows every county, it might be, oh yay. So these are the counties that have institutions. That's awesome. Okay, so let's see. So what we want to do is create a counties with institutions. Let's see, working GDF. Let's see what we have. This could be might as well be our counties with institutions data frame, but we don't really need any of this right now. So we're gonna create another chain of data frame. Counties with institutions equals working GDF, and we're gonna pass the list of variables that we care about. County name, share URM, geometry. And that's all we really need right now, right? Let's see, counties with institutions, head, just sanity checks. Perfect. So what we want now is this same thing, but for counties without institutions. And then we can do we can try to do it the spatial join way and see how, I don't know, change this to outer instead of inner, or some weird join. But that's unnecessarily complicated. If you already, it seems like it's more people are a little bit more versed in pandas and regular data analysis tools than geospatial data analysis tools, and we can use that to our advantage. We can make a list of these county names, these full names, and these are going to be our counties with institutions, and we can just use that to filter out from the contiguous United States, filter out the counties with institutions, and then we're going to end up with the counties without institutions, right? So let's see. First, list of counties with institutions, and you don't have to name your variables or something this long. With institutions equals it's gonna be it's actually gonna be counties with institutions name, and that's gonna return a series, and what we want is kind of a list. It's just the values, right? So list of, it's an array. instead of a pandas series, because the pandas series come with an index, and that's extra data that we don't need. And the way we check for counties without institutions, we're gonna create, so we have this list of counties with institutions. We're gonna create a list. We can do this one of two ways. We can use this to check that something is not in this list, or check something that is in this list. Let's try this. Let's try the first one. So we can do contiguous United States. Name is in list of counties with institutions, and that's going to return us a true false for each of them. And then we can see contiguous US head, so we know that this county is not there, this county is not there. Number 3, Lancaster County, that's the first one, and we know that it definitely is here, right? So what if we pass this, just make it a negative, just turn all falses into trues, all trues into falses, and it's the other way, right? So now this is a list of county filter for counties without institutions. We can just make this mask counties without institutions, bam, and then contiguous US with mask counties without institutions. But now number 3, Lancaster County, is not here, so these are counties without institutions, and we can save that as counties. Oh wait, so not tab autocomplete. Without, make space, institutions equals, bam. Oh, copy, because we're gonna do copy. And now we can just sanity check counties without institutions, plat. This should be the complement of the other one, right? Okay, so that kind of looks like the complement of this. Perfect. So now what we want to do is check out the statistics. You'll notice that this is way faster than everything we did in RQ1, and that's because we're borrowing this code, but also because we saved all the data work that we did earlier on. We already saved it onto the shape files. We don't need to do any of that anymore. So this is way faster. So now we have this, but the only statistics that we have for this, for each county, is share of underrepresented minorities. And we could do, what we could do is this: counties with institutions, grab share of underrepresented minorities, and give me the mean, right? So counties with institutions, the share of underrepresented minorities is 22% on average. Counties without institutions, share of underrepresented minorities, mean is, so in the counties without institutions, the share of underrepresented minorities is actually 18.17%. So it's lower. So in counties where there are no institutions, they tend to be less underrepresented minorities. Yes. That's interesting. Because if you remember on our RQ1, on our maps, it seems like the counties without institutions, remember our maps, it seems like there's only very few colleges in the counties where there's a majority underrepresented minority. And that you would think, I was like, okay, well, there's obviously, if there's no institutions, there's probably more underrepresented minorities. But that's not necessarily the same. This is about majority underrepresented institutions. I mean, majority underrepresented minority in a county, and this is about like all counties. So this starts to give you more details about the analysis, right? You start looking at there's more it's more nuanced than just counties with majority underrepresented groups are less likely to have institutions. Well, it's not as simple, right? So this is one way. So we already got some statistics, but now that we have this set up and we saw how easy it was to join data, now that we have this GeoID ready to go, what we could do is just ask Census Data Downloader for more data, right? We don't have to keep it just in terms of share underrepresented minorities. We can do Census Data Downloader year. What do we want? Median age, counties. Oh, year 2018. And actually, we can go on Census Data Downloader under tables, see what they have. So they have median household income, median age, we have race, we have veteran status, foreign born. That's interesting. Education, age, ancestry. So there's a lot of these, and you should spend some time looking at what you are interested in researching. And we have it by county, but you can definitely do by something else, right? Now you know how to do this. Maybe you want to do it by state. So we have median age. Let's do median household income too. Okay, it seemed, let's double check. Some seconds ago, so processed. Okay, yeah, median age and median household income. Awesome. So now we have this. You can put a little note to yourself. Run census data downloader to get median age and median household income. And now we can do median age equals PD read. CSV, just like we did the other one, is in external. It's in processed, and then it's in ACS 5 2018, probably, because these are standard names that they give. Median age. CSV, let's see. Yay! Okay, I'm just gonna use the same cell for median household income equals PD. Let's do all of that in lowercase. I don't want to keep using shift. Read CSV, external data, processed, ACS 5 2018, median household income, counties.csv. Awesome. Okay, so I accidentally click M here, so it turned into a markdown cell. I'm gonna go back to code. Median age. Let's see how this is looking. Okay, so it has median age by county, by GID, median age for males, median age for female, and state and the county, and median age. It has the median household income, the margin of error, state and county. Okay, so from these we want, let's just keep it to the median age, right? Okay, median age equals median age, and let's just keep GeoID, name, and median. And this is supposed to be a list, so you need 2 square brackets. And median household income, let's do median household income, and we need the GeoID, the name again, and the median income. Perfect. And you'll notice that both have the same names, and that's gonna be an issue if we want to join them all in one. So let's rename the columns. GeoID, name, median age, median household income, columns, GeoID, name, median age income. Okay, median age. Let's see how this is looking. Awesome. But you may remember that when we first get data from the census data downloader, let's check the D types. See, remember the GeoID is actually an integer, not a 5-character string. So we need to fix that GeoID. So we gotta do median age, GeoID, and I'm not gonna go too much into detail because we already did this. Median age. We could go to RQ1. First, we ask for it to be type string. We use the string accessor. We do the zfill function on it, and we're gonna do median household income to GeoID. Type string accessor, zfill 5. Oh, and this is because, see, this is the warning that I was telling you. Trying to set on a copy of a slice of a data frame, because it thinks that this is a slice of itself instead of like a copy. That's fine. Okay. So next thing, we gotta set this GeoID as the index, like we did before, right? Median age, set index GeoID, and we're just gonna do it in place equals true. Same with income and now we have median age. Perfect. And our working file is this: counties with institutions and counties without institutions. Counties with institutions, let's set index GeoID in place true. Same with counties without. Set index GeoID in place equals true. Awesome. And now we can do counties with institutions, join median age. It's gonna be on the index already. It's gonna be a left. Yeah, so it's only gonna keep those that appear on your left data frame. That means counties with institutions. It's gonna show on phone. Okay, it seems like this is working. Let's see. Dun, dun, dun. Oh, because they both have they both have this name column. Actually, we could just drop. Let me just drop that. let's just trust that GeoID is good, which you can. Median age, drop columns, name. Again, let's just do it in place to save some space. Median age dot drop columns equals name, in place is true. Perfect. And I just added that. And because this is returning a data frame, you can actually chain joins, and we can chain median age income. Perfect. And we can just counties with institutions and overwrite it. And we can do the same with counties without institutions. It can equals counties without join median age and join median age income. Boom. Counties with institutions. Just reality check it. Doesn't cost you anything. Perfect. So now we have this. We can do just like we did over here to check the mean of the counties for institutions that share underrepresented. We can do the same thing for median age, the average median age, which gets a little confusing, and the average median household income. But what we can also do is just take advantage of pandas, the analysis capabilities, and just go counties with institutions, describe. And this is going to provide you some summary statistics for every number column, anything that's a float or an integer, and it provides you this basic statistics. So you can see that the average share underrepresented minority is 22%, like we knew before, but the standard deviation is 19%, so it varies a lot. It can go, it covers 95% of the counties fall within 3%, so 22 minus 19, so 3% and 40%, so 22 plus 19, 41%. Yeah, let's go with that. Median age 39 years old, counties with institutions. Median household income $54,000 a year. It varies around $15,000. Okay, and it comes with minimum. So the youngest median age county, the median age. Oh wait, 21 years old. Oh, there's a county in counties with institutions where the median age is a 21-year-old, 22-year-old, and they make $20,000 a year. Oh, that's interesting. I wonder which one. We can check actually in a bit. Counties without institutions. Let's do the same. So underrepresented, the average underrepresented is 18%, but it varies just as much as 19%. That's interesting. So it can go up to pretty much the same. The median age is 43 years old, so that's 4 years difference. So there's slightly older populations, but it varies a little more. Median household income is $49,000 versus $54,000. That's interesting. And it varies even less, so $12,000 instead of $15,000. Huh. Now you can start asking some really interesting policy questions. What's going on here? The max is larger. That doesn't tell us much because it varies a lot. Wait, no, median household. Oh, wow. Yeah, there's counties with really young people. What's going on? Okay, so well, this is one way to look at this. You got the summary statistics, and now you have what's important is that you created a subset of counties that you attached some data to it, and then you used a spatial joint to check whether that county had any of these points over here. And these points over here, we use institutions, but you can look at other anything that you can think of. I mean, schools are pretty much everywhere, but maybe there's counties without elementary schools or middle schools or more than one high school. You can come up with any questions like that. Maybe certain hospitals or certain services. You can you can now use this same workflow to look at, okay, I have these counties, I have these shapes, I have these polygons, right? And it can be tracks, it can be counties, it can be states, it can be countries, um, and then I have these points. It can be hospitals, it can be schools, it can be taco stands, it can be anything. And then I want to see which of these polygons don't have any of these points in them and which do. Or I want to see like RQ1. I was like, where, like, based on some characteristic over here, if we use share underrepresented, if there's a majority underrepresented minorities in this county, what type of school, what type of points are there in those? So you can now RQ1 and RQ2 help you develop that workflow. Can you check if they're in? Let's look at the polygons. Are there any of these points in them? Okay, well, let's look at some characteristic of the polygons, and then grab the points that appear in those counties, in those polygons with those characteristics, and check out the characteristics of those points. That makes sense. Hopefully that makes sense. If not, you can always definitely put an issue on the GitHub repo. And I know if you sign up for this workshop, we're gonna have a Q&A at some point. Or reach out to me on Twitter and be like, that did not make sense. Now that you have done this and you saw that how easy it was to just use census data downloader, then read it into it, just grab the column that you actually care about. You should care about all of these because this is maybe more for stats nerds. Grab the columns that you care about, fix the GeoID because it's not an integer and it comes automatically. This is just because the nature of the workflow that census data downloader is doing behind the scenes. Set up the GeoID and then just merge it into this other subset that you already put together. And you can do a lot of things. Internet, this is something really interesting. On my other workshop last year for 2019, we looked at the digital divide using census data, and it might be this. Actually, we used IPEDS, which, if you're interested in all data census, is an amazing place to get data. There is IPEDS USA, which uses census and ACS, American Survey Data. But if you're interested in international stuff, they have like a collection, nearly 100 countries' censuses. It is great, and they harmonize data across years. So if the questions vary a little bit, they'll come up with a question that makes sense for both and then just aggregate it to it. But not only do they harmonize data, like tabular data like that, and questions and survey answers, they also harmonize geographies. So there's certain countries. The example they used, I think it was Congo, in one of their webinars, and there's like 5 or 6 regions in them that have change in shape overall, like the state or whatever secondary geographic level is, and they harmonize it across time, so you can come up with some really interesting statistics. IPEDS, it uses ACS data at the individual level, so not up to the county level. You're just gonna have to aggregate back, but that's what you can. That's what we do in my other workshop. So you can just look up Sergio Sanchez, PyCon 2019. Okay, awesome. So that's research question number 2. Let's move to research question number 3. All right, let's get to research question number 3, the last task in our tutorial today. We're going to be creating some education desert maps. We're going to see if you create these 10, 25, and 50 mile radii radiuses. It's not radiuses. You put a 50-mile radius around each institution, each higher education institution in the whole United States. What parts of the country are left out, and what are some of the characteristics of those? And this one, we're gonna do it with counties, so we're gonna be taking like chunks of the counties out. So if your part of the county is inside this 50-mile radius, it's gonna be left out. You'll see it'll make more sense once we go through it. But if you wanna do more granular units like census tracts, zip codes, there's an interesting debate going on around whether or not you should use zip codes in social science, like on geospatial analysis, because it's not an actual shape. Zip codes are, first of all, they change more often than you'd think, and they actually, it's not like a shape, it's lines. It's not an area, it's not a polygon, it's lines that the USPS uses. There's a lot going on. I saw a paper online. I'll share it. I'll put it on the repo if you're interested, on the README file. It's kind of interesting. Let's do 25, not 20 miles. And these numbers are not necessarily random. There's a study here in California. I think I mentioned it earlier in this tutorial. Most people go to schools nearby where they live, even higher education schools. And it was in California, so like UC students for the University of California, their median distance between their between the place they live and the college they went to was like, the median distance was like 50 miles. For CSUs, for state schools, it was like around 20-25 miles, and for community colleges it was 10. So that's why I chose these numbers, and I'll put a link on the README too for that paper. It was by UCLA. It was a while ago. Around higher education institutions, what parts of the country are left out? Okay, perfect. We're gonna borrow the same first three, actually 4, because we're gonna be using this same data too, since we already prepared it on research question 1. We're gonna do copy. You can also click the key C, the letter C, or V for paste, or I'm gonna do paste. I'm gonna read this, I'm gonna read this, check out the data that we have. We're gonna read in the data. Okay, and now that we have this, let's check out super quickly. Reality check, geo institutions. This is essentially what we're gonna be using to create the radii, right? These are points, and what we want is to create, just like this, those little circles, create a circle around a point. The only difference is that we want to be able to specify how large the circle is in real distance, right? So 10 miles in the real world, not necessarily like 1 or 2 or 3 pixels on a picture. So the way we do that is, this is why it's so important that we added CRS information to our GeoDataFrame. If you check this, you can see that we're using CRS EPSG 4269, and it's using latitude and longitude. It's using degrees as its unit of measure, right? And what we want is to be able to use the information that we have where they are in the world and create a radius around it. And the way we measure that, we said it was going to be 10 miles, 25 miles, 50 miles. And you could do, if you're really good at this, you could do the math and figure out, okay, well, 10 miles is 0.0 whatever degrees in latitude and 0.0 blah 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 degrees in longitude, and then use that to create a buffer around each point. But what we're gonna do is we're gonna change this CRS, the units. We're gonna transform our points from one coordinate system into another that uses units much manageable for this specific task. We're gonna be using we want meters as that unit of measure. And one way to do this is I'm gonna copy this so you can see EPSG. Should have put space in between because I think it's something else. So EPSG.io is your best friend when you're trying to figure out these type of things. So 4269, you can see center coordinates, bounds, etc., some more information. And what we want is to switch to a meter system. I don't expect you to know this from the top of your head. It's 3857. These are two of the most common, more or less, projections. So what this is doing is, and this is what Google Maps, OpenStreetMap, ArcGIS, S3 Bing use kind of like by default. We're using this other system, EPSG 3857, because let me see. Oh, I should have checked this already. I know that this one specifically uses meters. That's why we're using it. But I remember, where does it say? Geodetic system. The unit of measure is meters. That's what we're using. That's what we're using it. You can kind of guess that from here, more or less. Isn't that? I don't even have the excuse that this is a live demo because this is being recorded. I could have checked before. I apologize. Just on this one, trust me, or look up EPSG 3857 on your free time. We're gonna be transforming it into this new coordinate system because it uses meters as the unit of measure, and that way when we ask GeoPandas to create buffers around a point, which it does mathematically on looking at a point and then just doing some math around it, the units, it actually translates into what we want when we're creating this, because otherwise we would have to specify specific, like the degrees, like I just mentioned. So the way to do this is Geo Institutions to CRS, Shift Tab. You can specify a CRS system of projection pyproj.crs, which is not great. But now you can specify just EPSG equals this, right? EPSG equals 3857. And before we do that, actually, where is it? Geo institutions.head. You see this geometry. The point is at negative 108 and 48. That's the longitudinal latitude. If we do it like this, we transform it. It changes those degrees into meters, right? That's exactly what we want. And you can see that this is returning a data frame, so we can do in place equals true, or we can assign it to itself. We're just gonna do this for the sake of speed. And now that we have this, Geo Institutions saved already as this, what we're gonna do is create what GeoPandas calls a buffer. Geometric manipulations. You saw this earlier in RQ2 when I was looking at for the merging data. This is something else. This is what we're looking at, buffers. The way to do that is distance, we're gonna pass it, if we do 100 for example, it creates a polygon. And you'll notice here that, let me show you that head. It goes from this number 12,106,864 to still 12,106,764. So it created a 100 meter buffer, which is what we want, but we don't want it to be 100 meters. We want it to be 10 miles. We want it to be 25 miles. I want it to be 50 miles. And a mile is 1,609 meters. Right? So what we're gonna do is just do some math here. 10 times miles, just transforming it. And that's it. And now you can see it's 12 million, but now it went down to 90,000 instead of the 106,000, because it's creating that circle, those circles. Okay, and the way we're gonna do this is transforming only the geometry series, and is returning a series, as you can see. So what we're gonna do is first make copies, because we want different data frames. We're gonna do institutions 10 mile, and it's gonna be geo institutions. It's going to be a copy. Institutions 25 mile, geo institutions, copy. Institutions 50 mile. First we create all these copies, and we're gonna do another one. If you're signed up here, if you click A, it creates a cell above you, and if you click B, it creates a cell below the cell that you have signed up. I mean, you have selected. And the way we're gonna do this is institutions 10 mile. The geometry, which is what we're transforming, is gonna be institutions 10 mile, just for consistency. Geometry, it could be geo institutions, it's gonna be the same because they all share the same geometry right now. Buffer 10 miles, right? And we're gonna do the same for the 25 mile. Geometry, 25 miles, institutions 50 miles, geometry 50 miles, geometry 50 miles, right? Done. And again, I'm just gonna move this over here so we have, so it makes sense that this is how we're running this. Institutions 10 mile. Now we can do reality check. Ta-da. Now these are not points, right? So when it was point, GeoPandas a matplotlib underneath. The hood is it's just assigning a specific size to the point. It's just 1 or 2 or 3 pixels, whatever the default is. But these are no longer points. These are polygons. These are circles. So it displays it by its true size, quote unquote. And you can see also that the legend has changed here because it's now using the meters instead of the degrees, right? So reality checks, one way to think about it. Let's see institutions. We're gonna skip 25. It's the same thing. It's just for the sake of time. Let's do 50. Now it looks to have, you have 50 mile radii, around each institution, and you can still see, okay, so most of this half of the country is covered, but there's not a lot going on here, especially here. And it kind of makes sense. There's not I think the Rockies are here, and it's just this is much more densely populated. But let's check it out. Let's see what this is all about. Let's see what the answer really is. What parts of the country are left out, and then we can look into some of the characteristics of those parts of the country that are left out. What we're gonna do is put those institutions, those circles, on top of a map that we have, and we're gonna use those to filter out the areas that are inside this. So we can do this. We can do an intersection. So an intersection of the county shapes, and then the circles that are the radii of each institution, and show me only the parts where they overlap. So you can actually see, obviously, because they're all inside the counties and inside the country, you would only see the areas of the country that are inside that radius, right? So that's what we're doing. We're taking advantage of this instead of doing the spatial join and putting it all together. We're just overlaying geometries. And the other thing that we're gonna do is the difference. So we're gonna have a map of the US below the county level map, and then we're gonna take out all the areas that are actually taken that are within 50 mile in a 50-mile radius from the institutions. That way we can see what parts of the country are left out of these of this services, the higher education institution. So intersection and difference, those are the ones that we're looking at. And the way to do this is actually really simple. GPD, overlay. And this is actually surprisingly simple because one, there's the function already. They already know it's going to be overlay. But two, you already did all the work over here. You already cleaned the data. You already processed the data. You read, processed, and saved the data. And you have it already in a geo format, geospatial format. And you also already added metadata to your geodata frames. You made sure that this wasn't just a bunch of numbers that GeoPandas wouldn't know what to do with. You added this early on in the process, and that's what allows this to happen so easily. To do all this math would be impossible really if you hadn't assigned a CRS earlier in the process. So overlay, we're gonna do, what did we save it as? Contiguous US. Contiguous US, it's gonna be our base, and then we're gonna overlay the institutions, 10-mile radius. And let's do shift tab, how. So by default is the intersection, right? So let's see what this looks like. And actually, if you run this, it's doing the math behind it, right? It's gonna return a geodata frame that has the geometries already fixed, right? And what you can see here is you didn't get anything back, right? So first mistake that we did is try to overlay a geodata frame in IPEDS 4267, did we say? 4269, which uses degrees, and we try to put another geodata frame with IPEDS 3857, which is meters as its unit of measure, on top of each other. So how would you even know how to do that? How would pandas know? How would GeoPandas know how to do that? So the way we're going to do this is institutions to CRS IPEDS equals 4267. We're going to do in place. And because when you do this, when you do the 2CRS, it returns a geodata frame, you could technically do it here. 4269, not 67. So that would work, but then you would have to do that every time you're calling this, and it's not. Why do that? Right, institutions, 5 now, to CRS, PSG, 4269. Okay, so this is what would happen. It would create a polygon. It would return a polygon that, I mean, at first sight you can't really see what's going on, but this is a polygon of all the areas that are different, right, based on this definition. And it's hard to see this, but if it's good that we get the geodata frame in return, because then you can save this and use it for something else. If you want to save this as a shape file of a bunch of counties with chunks taken out based on like whatever you're choosing to analyze, that's why you want that information back, right? But because what we're trying to do is just visually see what's happening, just a reality check. Let's see if what we're doing is right, if it is difference, and maybe it's not difference, maybe it's geometric difference, or symmetrical difference, or an intersection. I mean, it makes sense, right? You're only showing the ones where they overlap. And what you want is, I mean, where they intersect, which makes sense if the way you just did. Sorry, that took me. So you're only showing where they intersect, like we mentioned. It's only the areas that are covered by those 10-mile radii, which is essentially the same as plotting the 10-mile radius on top of each other. But what if we try how difference? So what's the difference between these geometries? If you have a bunch of polygons and you have a bunch of other polygons on top, the difference would be the area that they don't overlap in, right? The intersection is that one area where they overlap. The difference is the rest. This is what we got. This is what we're asking for now. Yay. So now you can see it's, like we mentioned, it's the shape of the counties, a map of counties of the United States, and then you start kind of like scooping out all those 10-mile radiuses, a 10-mile radius around each point, each of the higher education institutions. And so now that we have that, and that you saw that GPT overlay is returning a geodata frame, what we want is to explore that geodata frame, right? I want to create cooler maps off of this. So we're going to do 10 miles. It's going to be GPD overlay, contiguous US institutions, 10 miles, how equals difference. Because we want to make sure that we get the difference and not the intersection like we did at first. We're going to do 25 miles. GPD overlay, US, institutions 25 miles out equals difference. $50 equals GPT overlay to US institutions 50 miles out. Please don't judge me for my use of double quotes and single quotes. It's honestly so random, and I would think that I have a preference too, but no, it's honestly, sometimes I do one and sometimes I do the other, and I don't even think about it. This might take a little bit because the overlay, you saw how long it took for this to first happen, right? It's doing a lot of math behind the scenes. Okay, and then we're gonna take a look at our geo data frames that are returned. And then maybe we'll be good to go. Let's get ready. 10 miles ahead. Shift enter. Shift return. This one takes a little longer because again, you saw how long it took for this one. I'm doing it 3 times. Dun, 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 dun. There you go. So there's 10 miles. Now we have our geometry with the share underrepresented, but this geometry they already scooped out all these areas. Watch 50 miles plot. There you go. So you see how this is already what's left of this overlay. And what we want to do is, oh no, yeah, let's leave that there. What we want to do now is use this, just make it a little prettier so we can see, for example, the share underrepresented. More visually, so it makes sense, so we can see. So we can visually make sense of what areas are being left out, right? So we're gonna do GP core path 10 miles. The hue is gonna be share under because it cuts at 10. We're gonna specify, and I don't expect you to know this off the top of your head. This is matplotlib. This is not GeoPandas. It's just something that you can learn as you practice more. Fixed size is one of those things. These arguments, because I don't think I'll show you. Okay, there you go. So all of this is already taken out, but the lines are too thick, so it's covering all of that. Let's see if we specify. How can we specify? Maybe we can change the projection because it's also a little weird. Not weird. Let's make this prettier. We're gonna do projection. We're gonna do GCRS web Mercator, which is what we've been using for other ones. And we can use GCRS because we're doing it over here. We implemented it from GeoPandas. Again, I think it's this web Mercator thing that makes it take so it takes a little bit longer than usual. Might just take a little too long. We can get started with the rest. We have share underrepresented, but just like we did in RQ2, we might want to include household income and median age. So we can actually copy this code all the way to here, because this is where we joined it. We're gonna copy it. I'm gonna paste it over here. And we actually don't need to check this one. We already know that it works, so we're just gonna keep only the code that we need. So all of these, and we can, if you click on this side and not inside the cell, if you click here, you shift, click somewhere else. So you're highlighting all of these. You can do edit. Oh yeah, it's here. Merge, select cells. So we can just make it one big cell. There you go. See, it's starting to make sense. And you can, 10 miles is like, you can start to see some areas of the country here that there's definitely some people here that are not being, they're not even close to institution. We can even do, let's say 50. Hopefully this is faster because it's this thing over here. And then we can run all this, and we're gonna have counties with institution. Oh wait, that's not what we needed. We don't need counties with institution, but we're gonna have median age and median age income ready to be merged, right? We're gonna run that too. And what we're gonna do is, there you go. So we start, you don't really want that because it's just taking chunks out. But what we're gonna do, we're gonna make this pretty. We're gonna make this actually usable. But you start to see what we're trying to accomplish. It's created this map of all of this in the United States. All these areas that you can actually see are parts that exist outside of the 50-mile radius of each college institution or any higher education institution. So if you live here, there's not a higher education institution in quite a long way, right? And that could be or could not be a problem depending on how you feel about higher education. Okay, so now we have median age because we shared the code. You can grab it from over there. This is how it looks like. What we're gonna do is, let's stick to 25, which is kind of reasonable. Like if you if you don't want to go too far away from college. 25 miles. So this is what this looks like. We need to set its index to GeoID. We're gonna do it anyways. And 25 miles. Join median age, and like we saw earlier, we can change these because they have it's returning a data frame, so you can just chain them. Median age income, and there you go. So now you have this. We're gonna do 25 miles, just overwrite it. And what we can do now is 25 miles. What we want to do is do something like this, but instead of share underrepresented, we can do now with median age and see what the age of people that live here look like. And what we can do is overlay maps, right? So we have our contiguous US that covers everything. That's a map of everything. We can use that as a base layer, and then we can just throw this on top so we can actually see the country, right? And the way to do that is we're gonna create an axis. This is some matplotlib syntax. We're creating an axis, and we're gonna create first I can't type today, a polyplot. So it's plotting polygons, and we're gonna pass the df is gonna be contiguous US. The projection is gonna be GCRS web Mercator. The Z order, which you can't see here, is one of these keyword arguments. Is just specify where it goes. We're going to specify that we want it below, so it's all the way in the back. Let's specify again the extent, fixed size, and all this. That's not something we need to worry about. Fixed size, yeah, but these keyword arguments, those come from matplotlib, so that's not something we're gonna cover here. So you're just gonna have to trust me that these exist. It's gonna be line width equals 1. We're gonna do edge color. We're gonna do it white. That's one. Just makes sense. Those lines that we saw earlier that they were all black. We don't want that. We want white. And that line width, we want it smaller. We want it just a size of 1. Face color for the polygons, we want, what do we want? Still light gray. And the fixed size is gonna be again, and then you pass a tuple is height and width and height. I always specify 1212. It's not actually making it 1212. It's doing. It's not because the country is not a square. That's what I'm trying to say. I'm just gonna make this a little bit easier to read. And actually, let's see how this would look. If this all worked out, you would just see a map of the United States with lines showing the counties, and that's going to be our base layer. Now we're going to throw this choropleth on top of it. Let's copy this code too. But we don't want to do 50 miles, let's do 25. miles. And actually we don't need the projection because it's already specified. This one, which is the base, same with the fixed size. I don't need that because there's already a figure specified. All we gotta do is actually specify which axis we want it on, and it's gonna be on that axis, on that figure that we showed earlier. Just gonna save this just to make sure that we have it. Oh, there you go. Okay, so that makes sense, right? This is what we wanted. This is going to be our base layer. And now that it has already done it once, hopefully it's a little faster. So what we want is we have this base layer so that we don't end up looking with this like floating blob. But we're going to grab this and plot it on top of this so we can actually see to have some context. Dun, 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 dun. We'll see how long that takes. And in the meantime, we're gonna do I'm gonna show you how to do a more advanced way to do this. Okay, so let's start working on that in the meantime. So the way we did this, so we're only focusing on the 25 miles. We're going to create a 25 miles overlay, but instead of the difference, which is this, we want the intersect, which is what we got in the first place, right? So we're going to do enter, and we're doing it this way instead of just plotting the actual institutions, the radii. The polygons of the institutions with the 25-mile radius around them, because what we want is the information from the counties, from the contiguous US data frame. So we want a county shape, except we just want to drop everything that's not inside that radius. Yeah. So because this is the default, we can actually just delete this. And it's going to create that geo data frame. And now if we run this, ta-da! Okay, so this is how it's starting to look like. These are the areas of the country that don't have a higher education institution within 25 miles. So if you live here, there's nothing nearby. But if you live here, you might be like 26 miles away from a college institution, a higher education institution. So what we're going to do is create that same thing, but the opposite after this runs. This is anticlimactic because this is the end of the lesson. This is we're gonna finally come up with the education deserts. I mean, this is one education desert. meantime, we can see if oh, this is not it. It's not the Guardian. Sorry, the Chronicle. No, not this. This is what we're looking at. Makes sense, huh? So this is what we did, what they did. Oh, they just did that. This is what we just did, except they're using census blocks instead of counties. Let's scroll down. See? There you go. Areas within 60-minute drive from college. That's a slightly different math, but this is pretty much what we just did. Wow. Let me just stop this and then just move it again. Wow, seriously? Well, I do recommend you read this. This is also part of, if you sign up for this, you probably saw this, specifically this image in the tutorial page, and that's what you just learned how to do, except they're using census blocks, which is very useful information. It's much more granular, which you can still do, just like we did with counties. You can just go get the shape files for census blocks, and actually if you do census, the census data downloader, you can do that with census data downloader. You can see that you can also use, they have congressional districts, just kind of interesting, elementary school districts, cool. Regions, states, tracks, census tracks. So you could do that and do exactly this, make exactly the same map, and that's a challenge for you. We did it with counties. Try to do the same, but with census tracts. Then go find the census tract tiger web line files from the census, the shape files. Throw them on the same project, and just like we did here, just like data external, just like I threw in the county zip file, just throw in the census tracts file and run the same workflow, do the same thing, except for census tracts instead of counties. Download the data just like you did this. Let's see how long that takes. Census data downloader, year 2018. Let's do median age because that's fast. Median age tracks. Oh, it might not be year 2018. That's the other thing. Census tracts, because it's such granular data, they can't just give you a lot of data for privacy issues. So we do those for privacy issues, and because the ACS, the American Community Survey, does samples of the population data. It's not like the census. They only survey, is it 1%? I think 1% of the country, and from that they make their estimates. But census tracts are so granular that we only use census data, like census year data, like the decennial census, which you should go fill out if you haven't. Oh, there you go. Bam. So now you can see these are the areas that will be the complement of this. So these are the areas that don't have a 25 higher education institution within 25 miles. These are the areas that do. You can use these in your maps, and you can do some analysis. We already ran the statistical analysis. We already saw the statistics for each county. We already saw where the median age, the median household income, the share of underrepresented minorities in each of those counties. But now you can actually display it in a cool way. Just like this is actually kind of like this is supposed to be. Let's go all the way to the top. This. Perfect. There you go. Thank you so much for attending Virtual PyCon 2020, for learning some geospatial data analysis, some geospatial public policy analysis with me. My name is Sergio Sanchez. Just one last thing. Remember that you can go to the GitHub repository for this at github.com/checos, and then not repositories, github.com/checos. It's gonna be right here. It's gonna be the second one, right up top. This is where you're gonna find all the information, the code, the solutions, the solution. I'm gonna add all these to the solutions folder, and I'm gonna add extra information in between, so like markdown and links, and like why are we doing this. So the link to the overlay, the link to merging data, etc., etc. There is, just like we did here, just like I did this workshop, there's also a workshop I did last year for analyzing census data, and that one we use IPEDS data, like I showed you earlier, and that's individual level data. We aggregate it all the way to county level to see which counties have a bigger digital divide, who has access to the internet, who doesn't have access to the internet, what are the demographics of it. And yeah, thank you so much for watching this video. I know it's been a long time. Hopefully you didn't do this in one sitting, because that's a lot, but if you do, remember, if you do, you're good to go. Probably your kernel didn't die, but if you didn't, remember, you can just make sure you download your notebooks and you throw them back in there. Or you can even fork this. You probably can. I can't do it because it's my own repo. But you can fork the repository and then just change the my binder link. And here, you can just change this little part to match your username and the name that you give it. It's probably the same. I think it's the same. And it will spin up a my binder instance for you, and then you can just then throw those notebooks into your own GitHub repository, and you're good to go. Again, thank you so much. Hopefully you learned something. Remember, if there's any questions, feel free to submit an issue. I'll be checking those, and I'll try to be as helpful as possible. Thank you so much. See you around.